Before the Big Bang, before there was light, matter, or time, the universe did not exist as we see it now. There were no stars, galaxies, atoms, or particles. Then, the universe began to expand from a state of very high density and temperature. Space and time came into existence. Subatomic particles formed and moved outward, creating the early conditions that would later lead to the formation of galaxies, planets, and living organisms. Was there a state of pure energy waiting to expand? Could time have repeated endlessly, with universes forming and collapsing in a continuous cycle? Or did the concept of before have no meaning at all? Before we begin, let us know in the comments below where in the world you're watching from and what time it is for you now. Then, settle in as we explore the biggest mystery about the universe. In the very beginning, the universe was a place of unimaginable intensity, a world of extremes unlike anything we experience today. This first stage is known as the Planck era, and it lasted from the exact moment of the Big Bang to about 1/10,000,000,000,000,000,000,000,000th of a second later. That is, from 0 to roughly 10 to the power of -43 seconds. During this incredibly tiny moment of time, the universe was smaller than an atom, hotter than anything we can ever make, and filled with more energy than we can even begin to understand. Everything, space, time, matter, and energy, was squeezed together in a thick, boiling mix of pure potential. The temperature was thought to be around 10 octillion degrees Celsius. That's the number 1 followed by 27 zeros. At that point, the 4 basic forces we know today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were not separate. Instead, they were joined together into one single, unknown superforce. That means the laws of physics, as we know them, didn't yet exist in their normal forms. The universe worked under rules that go beyond our logic, making it very hard for scientists to explain with what we currently know. Instead of solid particles like atoms or even protons and neutrons, the universe was filled with a strange moving mix of pure energy and radiation. Tiny particles like quarks and electrons were appearing and disappearing, created and destroyed in the blink of an eye. Matter as we know it, everything from stars to people, didn't exist yet. The universe was more like a hot, glowing soup of pure energy, where the rules of space and time were still forming. As this violent environment slowly began to cool, something amazing happened. The once joined force began to split apart. This marked the end of the Planck era and the start of the next stage, called the Grand Unification era. During this change, the different forces started to separate, and the building blocks of matter slowly began to form. But the Planck era remains one of the biggest mysteries in science. Even though it lasted for such a short time, it set the base for everything that came after. Understanding what happened during this time could help scientists answer some of the deepest questions about the universe, like how space and time themselves came into being. One of the main problems is that the normal laws of physics don't work at this scale. That's why scientists are looking for a theory of quantum gravity, which would combine Einstein's theory of general relativity, which explains gravity, with quantum mechanics, which explains how tiny particles act. If such a theory is found, it could finally reveal the secrets of the universe's birth. During the Planck era, space and time themselves may have acted in strange and unpredictable ways. Today we think of time as flowing smoothly, like a river, and space as a steady background with 3 known dimensions. But at this tiny level, time might have moved in little steps or flashes, not as a smooth flow. Space too might have been so twisted and tight that it's impossible to separate it from time. In fact, the difference between time and space may not have existed at all in the way we understand them now. Physicists think that at the Planck scale, space-time was not smooth but shaky and foamy, constantly changing because of quantum uncertainty. Think of it not as a calm ocean, but as a bubbling, unpredictable sea. This kind of reality is so strange to us that it challenges even the smartest scientific minds. As the universe grew and cooled, the once chaotic space-time began to calm down, and the different forces separated. Space and time became more ordered and familiar. This change opened the way for all the amazing things that would follow, like the creation of atoms, stars, galaxies, and eventually life. To understand this early part of the universe's story, scientists study a field called high-energy physics. This branch of science looks at how particles behave at energy levels far beyond anything we meet in daily life. Using huge machines like the Large Hadron Collider, researchers crash particles together at almost the speed of light, recreating conditions similar to those just after the Big Bang. These experiments help scientists learn how particles interact, how the universe's forces acted when they were still joined, and what kinds of matter might have existed in those first tiny moments of time. High-energy physics also supports ideas like cosmic inflation, the idea that right after the Big Bang, the universe grew faster than the speed of light for a very short time. This idea helps explain why the universe today looks so smooth and evenly spread out. By studying particle crashes and the traces they leave behind, scientists can test ideas about how the early universe behaved. They can even explore quantum fluctuations, the tiny changes in energy that may have led to galaxies billions of years later. But because we can't go back in time or directly see the Planck era, researchers depend on clever tools like cosmic microwave background radiation, the faint leftover glow of the Big Bang still visible today. This light, which is over 13 billion years old, holds tiny ripples that give clues about how matter was spread out in the young universe. Computer models also play an important role. By using the laws of physics and changing different starting settings, scientists can rebuild what might have happened in the first few moments after the Big Bang. These models show how the simplest particles formed, how they joined to make atoms, and finally how stars and galaxies took shape. Another exciting tool in the search to understand the early universe is gravitational waves, ripples in spacetime caused by powerful cosmic events. If scientists can detect gravitational waves from the earliest times, they could uncover secrets hidden in the fabric of the universe itself. About 3 minutes after the Big Bang, something amazing happened. The universe had cooled enough for quarks to stick together and form protons and neutrons. These particles then started to form the first simple elements, like hydrogen and helium, in a process known as Big Bang nucleosynthesis. This was the start of matter as we know it. In the earliest moments after the universe was born, something remarkable happened. A delicate balance between hydrogen and helium, two of the lightest and most important elements, was set in place. These elements formed in just the first few minutes after the Big Bang and would go on to become the building blocks of everything: stars, galaxies, and even the atoms in our bodies. The amount of each element made during that short time helped decide how the universe would grow and change. At that time, the universe was still very young, just a few minutes old, but the forces of nature were already shaping it. The temperature was extremely high, and matter was packed together very tightly. These two factors, heat and density, played a big role in shaping the future of the universe. Where the universe was a bit denser, gravity pulled more matter together. Over billions of years, these thick areas collapsed under their own weight, forming stars, galaxies, and clusters of galaxies. Meanwhile, places with less density didn't form anything. They just spread out and cooled, becoming the huge empty spaces between galaxies, cosmic voids. By studying how heat and density acted back then, scientists today can study a faint glow that still fills the universe. This weak light is called the cosmic microwave background radiation, and it is a leftover trace of the Big Bang. It first appeared about 387,000 years after the universe began, when things had cooled enough for atoms to form and light could move freely through space. Even though this light is very weak today, it still carries important clues from that ancient time. When scientists study this radiation, they're not just looking at the past, they're finding answers about the very fabric of our reality. These answers can be better understood through quantum mechanics, a field of science that studies how the tiniest particles act in strange and surprising ways. At the quantum level, things don't follow the rules we see in everyday life. Particles can be in many places at once, or exist in several states at the same time, until someone observes them. This idea leads to a fascinating question. Before the universe began, could reality itself have been just a swirling field of possibilities? Not a solid, fixed thing, but a cloud of quantum potential waiting to take shape. This is where the idea of quantum fluctuations comes in. Even in what seems like total emptiness, tiny bursts of energy can suddenly appear and disappear. These small bursts might have started the birth of the universe itself. Before the Big Bang, there may not have been a universe in the normal sense. No space, no time, just a bubbling field of quantum energy. It's possible that from this strange and invisible energy, the Big Bang burst into being. Some bold ideas go even further. The multiverse theory, for example, suggests that our universe is just one among endless others. In this view, there might be an infinite number of universes, each with different laws of physics, all existing at the same time. Ours may have just been one of many possible results from a quantum field so large and full that it gave birth to many different realities. If this is true, then our understanding of space, time, and even existence itself could be far more complex than we ever thought. One of the most exciting tools scientists have today to study the early universe is something called gravitational waves. These waves are like ripples in space and time, and they carry information from some of the most powerful and violent events in the universe. 100 years ago, Albert Einstein predicted they existed in his theory of general relativity, but it was only in the past few years that scientists finally found them directly, using very sensitive tools. These gravitational waves may have been made during the universe's first split second, in a moment called cosmic inflation, when space itself grew faster than the speed of light. By studying the waves left behind from this quick stretching, researchers can learn what the universe was like when it was just a tiny part of a second old. The strength and number of these waves might show what kinds of energy and forces were active at the start of time. But gravitational waves don't just come from the early universe, they also come from big events like the crashes of black holes and neutron stars. These space collisions send ripples through space that we can now detect, giving us a new way to study the universe. Each new finding brings us closer to knowing how stars and galaxies formed, how gravity works, and how the universe has changed over time. Gravitational wave science is still new, but it is already changing the way we see the universe. As scientists keep improving their tools and ideas, they may find even deeper secrets, maybe even what happened before the universe we know came into existence. This is an exciting new chapter in our search to understand everything around us. And all of this connects back to that dim, ancient glow, the cosmic background radiation. That soft light, which appeared almost 400,000 years after the Big Bang, is a picture of a universe that was just starting to take shape. At that time, the hot plasma cooled enough for atoms to form, and for the first time, light could move freely through space. This light still shines today, weak and cold, but full of information. When scientists map this radiation, they find small differences, tiny spots that are a little warmer or cooler. These differences show where matter was starting to come together and where it was spreading out. From this, we can tell that the early universe wasn't perfectly smooth. It had just enough unevenness to create all the stars and galaxies we see today. Some of the most interesting ideas in modern science, like string theory and the idea of many universes, suggest that our universe might not be the only one. In fact, there could be endless other universes, each with its own laws of physics. This opens up an amazing thought. Maybe the question of what happened before the Big Bang doesn't even make sense in the usual way we think about time. In these ideas, the Big Bang might not have been the beginning of everything, just the start of our universe's story. To explore this great mystery, scientists are studying the faint glow that still remains from the early universe, the cosmic microwave background radiation. This glow, which has been travelling across the universe for almost 14 billion years, is like a fingerprint left from the universe's first moments. By carefully studying its patterns, scientists are slowly putting together a picture of what the early universe looked like. Every new finding brings us a little closer to answering old questions that humans have asked for thousands of years. Where did we come from? What started it all? Why does the universe look the way it does? Thanks to amazing advances in technology, researchers now have tools that can measure the universe with great accuracy. These tools are helping them uncover details about the universe's childhood, and maybe even clues about what, if anything, existed before that first light appeared. One main focus is the study of the cosmic microwave background, the leftover glow of the Big Bang. By studying small temperature changes in this radiation, scientists can learn about how matter was spread out in the early universe. These findings are helping test a strong idea called inflation theory. This theory says that, in the blink of an eye after the Big Bang, the universe went through a sudden huge growth, faster than light itself. This quick expansion could explain why the universe looks so smooth and evenly spread today. But that's not the only idea scientists are testing. In the world of particle physics, scientists are using the Large Hadron Collider, the most powerful particle smasher on Earth. This amazing machine, located underground in Europe, crashes tiny particles together at nearly the speed of light. These crashes recreate the super-hot, super-dense conditions that existed just a tiny part of a second after the Big Bang. These crashes recreate the super-hot, super-dense conditions that existed just a tiny part of a second after the Big Bang. By watching how the smallest building blocks of matter act in these extreme conditions, physicists hope to unlock the secrets of how the universe began. If they find new particles or new forces, it could completely change what we think we know. Another exciting area is gravitational wave astronomy. In the year 2015, scientists made history by finding gravitational waves for the first time. Tiny ripples in space and time caused by huge cosmic events like black hole collisions. This discovery opened a whole new way of studying the universe. Now, by tracking these waves, scientists can look into events that happened very early in the universe's history, possibly even before light itself could move freely through space. Gravitational waves give us a completely new way of looking at how the universe was born and how it grew. Long before stars were born, before planets were formed, and even before light first shone across the universe, there was a mystery that has fascinated scientists and dreamers alike. What came before the Big Bang? It's a puzzle with no easy answers, one that has led to many exciting and mind-twisting ideas. One of the most important ideas in this area is called cosmic inflation. This idea doesn't exactly explain what happened before the Big Bang, but it does try to describe what happened in the first tiny moments after it. According to this thought, the universe suddenly grew at an unbelievable speed, far faster than the speed of light, during a time that lasted only a very small part of a second, much less than even a trillionth of a second. This fast growth set the stage for everything we see in the universe today. Although inflation focuses on what happened just after the beginning, it gives us clues about the strange conditions that might have existed right before our universe was born. Another big idea is the singularity theory. This idea suggests that everything, all space, matter, energy, and even time itself, may have been squeezed into a single point, smaller than an atom, with endless density. This point is called a singularity. At this level, the normal rules of physics simply stop working. Time may not have existed in any way we understand it today. In fact, there may have been no before at all, because time itself might have started with the Big Bang. But not everyone agrees that our universe had just one beginning. Some scientists believe in the idea of a cyclic universe. According to this idea, the universe doesn't just begin and end once. It goes through endless cycles of birth, growth, death, and rebirth. First, everything grows from a hot, dense state. After billions of years, it might shrink back in on itself, leading to what's called a big crunch. And from that, a new Big Bang may happen. This means our universe could be just one in a never-ending chain of universes, each with different versions of reality, each following its own path through time. Then there's the multiverse idea. This thought is even more surprising. It suggests that our universe might not be the only one. In fact, there could be countless other universes, each with different laws of physics, different forms of matter, and different kinds of reality. According to some versions of this idea, our Big Bang might have been just a small bubble that formed in a huge cosmic ocean filled with other bubbles, other universes. Maybe new universes appear all the time, and ours is just one tiny part of a much bigger whole. All of these ideas, inflation, singularity, cyclic universes, and multiverses, try to answer the same big question: where did everything come from? And one of the most interesting tools scientists use to explore this mystery is the strange world of quantum mechanics. Quantum mechanics is the science that explains how things work on the tiniest level, far smaller than atoms. In this world, particles and energy act in very strange and hard to predict ways. Things can appear and disappear without warning. One idea from quantum theory is called quantum fluctuations. These are tiny changes in energy that can happen even in what we think of as empty space. Scientists believe that these tiny changes might have helped shape the universe in its very first moments. Here's the interesting part. If space itself can bubble with energy, then maybe the universe didn't come from nothing after all, at least not in the way we usually think about nothing. Maybe what we call nothing is actually a strange field, full of energy and potential, waiting to burst into existence. These small energy bubbles could eventually grow into entire universes, including ours. This idea changes the way we think about creation. It suggests that nothing might not really be empty. Instead, it could be a lively, unseen sea of possibilities where entire worlds can form from sudden sparks of energy. And it doesn't stop there. These quantum fluctuations may still be happening today, shaping the universe in ways we don't fully understand. Some scientists believe the universe is still slowly growing because of these changes, and that small energy shifts continue to affect the future of everything, from galaxies to atoms. The multiverse idea adds yet another layer to this story. If there are many universes, each one could be shaped by different kinds of quantum changes. Some ideas even say that universes can form when two other universes crash into each other. If that's true, then maybe our universe was born not from a single spark, but from a cosmic crash, a kind of universe-making accident in an unimaginably huge space beyond our own. What's more, each of these universes might follow completely different rules. While our universe has certain constants, like the strength of gravity or the speed of light, other universes might have different values for these things. By studying these possibilities, scientists hope to understand how our own universe came to be and what the true ingredients for existence really are. Some experts even think the secret to what came before the Big Bang is hiding in these tiny quantum ripples spread across the vastness of the multiverse. By studying how these ripples act, both in theory and through detailed computer models, scientists hope to look backward, through time and beyond, to discover what may have existed before everything began. Finally, we return to the cyclic universe idea, one of the oldest and most poetic thoughts in all of space science. According to this view, the universe doesn't just have a beginning and an end. Instead, it is endless, always cycling through life, death, and rebirth. After growing for billions of years, the universe might someday stop growing and start to shrink. As it collapses, everything is squeezed into a dense, hot state, the kind that could lead to a new Big Bang. Then the cycle starts again. One version of this idea is called the oscillating universe model. In this view, the universe goes through endless patterns of stretching and squeezing, like the breath of some great being. With each new cycle, a new universe is born, carrying traces of the one that came before. Some ideas say that our universe didn't just start from one event and grow forever. In certain versions of a repeating or cyclic universe, especially ones linked to string theory, something amazing might be happening. Instead of the universe growing forever or ending in a frozen, dark death, it could be caught in a cosmic loop, growing, slowing down, shrinking, and then bouncing back to grow again. This cycle could happen over and over, like breathing in and out, never really starting or ending. This idea is called a cosmic bounce. Rather than the universe shrinking into a single point with endless heat and density, called a singularity, the process slows down and reverses before reaching that extreme. Then it bounces back and starts a new phase of growth. In this way, the universe could avoid total destruction and start fresh every time. It's like the phoenix of space, dying in fire only to rise again. This kind of thinking goes against the usual view, which says the universe started with the Big Bang and will either freeze forever or tear itself apart. But if the bounce idea is true, it means the universe could be endless, going through countless cycles of birth, death, and rebirth, always reshaping itself, making new worlds out of the remains of the old ones. Now, to really understand this, we need to go back to the very beginning, right after the Big Bang. One of the most exciting ideas in modern science is cosmic inflation. Think of a moment when the universe was still smaller than an atom. Then, in less than a trillionth of a second, it grew faster than the speed of light, becoming unimaginably large in an instant. This fast stretching helped smooth out the early universe, turning wild energy into the orderly cosmos we see today. This inflation happened within the tiniest part of a second, but it built the base for everything: galaxies, stars, planets, even life. Because of this event, the universe became large, mostly smooth, and ready for matter to form. But what about before inflation? What existed before that sudden burst of growth? This is where things get even more mysterious. Usual Big Bang ideas say that time and space began with the Big Bang, that before it, there was nothing. But inflation theory opens the door to other ideas. Some scientists believe the universe could have come from a different kind of reality entirely, such as a quantum vacuum, a strange field that exists even when there's no matter at all. In this vacuum, tiny changes might have started the birth of a whole new universe. In fact, our universe may not be alone. It might be just one of many, floating in a sea of universes, what scientists call a multiverse. In this multiverse, each universe could have its own laws of physics, its own types of particles, even its own kind of time. This leads to a mind-twisting thought. Maybe there wasn't a single beginning at all. Maybe time itself is more complicated than we thought. If there's no clear starting point, then what does before even mean? It makes us ask deep questions, not just about science, but about existence itself. As researchers study cosmic inflation and the strange behavior of the early universe, they aren't just looking for technical answers. They're exploring the nature of reality, how space and time are shaped, and whether the universe is one of many, endlessly changing. Let's return to the idea of singularities. These are places where the normal laws of physics completely stop working. The most well-known singularity is the one that supposedly existed at the start of the universe, when all matter and energy were squeezed into one tiny, endlessly dense point. This is what gave rise to the Big Bang about 13.8 billion years ago. Singularities also appear at the center of black holes, those frightening space traps from which nothing, not even light, can escape. When a huge star dies, it falls in on itself and becomes a black hole with a singularity at its core. These strange points show up again and again in our efforts to understand how the universe works. Some scientists think that singularities might actually help us understand what happened before the Big Bang, or what might come after the universe ends. For example, if black holes have singularities, maybe they also hide paths to new universes, or hints about the structure of space and time. So, these mysterious points are not just where the rules stop working. They may also be keys to solving the biggest mysteries in the universe. They push us to rethink everything we thought we knew about matter, energy, and the nature of existence. Now let's talk about string theory, one of the most interesting and difficult ideas in modern physics. It says that the smallest parts of the universe are not particles, like dots or points, but instead are tiny shaking strings. These strings are so small that we can't see them, but they may be the real building blocks of everything from atoms to galaxies. Even more amazing, string theory says that there might be extra dimensions, not just the 3 dimensions of space, length, width, and height, and one of time, but 10 or 11 dimensions in total. These extra dimensions could be rolled up so tightly that we don't notice them, but they might have played a big part in how the universe began. In some versions of string theory, the universe started not from nothing, but from a very different, very dense state where strings and dimensions moved together in disorder. From that wild state, the Big Bang might have burst into existence, not as a beginning, but as a change from one kind of reality to another. String theory also tries to connect everything we know, the pull of gravity, electricity and magnetism, and the forces inside atoms, into one single idea. That's a big deal. If we could understand how gravity and quantum mechanics fit together, we might finally understand what happened before the Big Bang, and maybe even what happens inside black holes. Right now, string theory is still being discussed. Not all scientists agree with it, and it hasn't been proven yet. But it gives us something powerful, a new way to think about the birth of the universe, not as a single explosion from nowhere, but as part of a bigger, richer, more mysterious reality that goes far beyond anything we can now see. And we must not forget about dark matter and dark energy, 2 unseen forces that shape the whole universe. Even though we can't see them, they're very important. Dark matter holds galaxies together with its gravity, while dark energy is making the universe spread out faster and faster. Together, dark matter and dark energy make up about 95% of everything in the universe. That's right, everything we can see, stars, planets, you, me, is only about 5% of what's out there. Dark matter and dark energy are 2 of the most mysterious and unseen forces in the universe, yet they play a huge role in shaping everything we see in space. Let's start with dark matter. Scientists believe it makes up about 27% of the whole universe. Even though we can't see it with our eyes or through telescopes, we know it's there because of the way it affects things around it, especially how it pulls on stars and galaxies with its gravity. In fact, dark matter acts like an invisible web, holding galaxies together. Without it, stars would fly apart instead of staying in neat spiral shapes, and galaxies wouldn't be able to keep their form. everything would just drift away into empty space. This unseen material doesn't shine, reflect, or absorb light, which is why it's called dark. Scientists found it not by seeing it directly, but by noticing strange movements of stars and galaxies that couldn't be explained by the matter we can see. Without dark matter, the universe would look completely different, a scattered, messy place rather than the beautiful and organized structures we see today. On the other hand, there's dark energy, which is even more mysterious. It's thought to make up around 73% of the universe. While dark matter pulls things together with gravity, dark energy does the opposite. It pushes things apart. It's the strange force that makes the universe expand faster and faster over time. This surprising speed up was first found in the late 20th century, when astronomers watched faraway exploding stars known as supernovae. These stars were moving away from us more quickly than anyone had expected, and that made scientists realize that something powerful, something unseen, was pushing the universe's expansion. That something was called dark energy. Even today, no one really knows what dark energy is. It goes against the rules of gravity as we once understood them, and it forces scientists to rethink everything we thought we knew about space, time, and the universe itself. When you put both dark matter and dark energy together, they make up about 95% of the universe. That means all the planets, stars, galaxies, gas clouds, and people, everything we can actually see, make up only about 5% of the whole universe. After the Big Bang, which happened around 13.8 billion years ago, dark matter helped pull normal matter together to form the first stars and galaxies. But as the universe kept spreading out, dark energy slowly became stronger than gravity. Over time, it began pushing galaxies farther apart, changing the structure and future of the whole universe. This push and pull between dark matter and dark energy shows us that the universe is not just a quiet place of stars floating in space. It's a lively, always changing arena where unseen forces are shaping the fate of everything. And that brings us to a truly amazing idea: the possibility of baby universes. This idea is one of the most interesting parts of modern cosmology. It comes from scientists' attempts to understand how our universe began, and whether it's the only one that exists. The idea of baby universes suggests that our universe might not be alone. Just like a tree might drop seeds to grow new trees, the universe might give birth to smaller, self-contained universes. These baby universes could each have their own sets of physical laws, different from the ones we know. This matches the idea of cosmic inflation, which says that space spread out extremely fast right after the Big Bang. During this quick expansion, it's possible that small pockets of space broke off and began growing into their own separate universes. Some scientists believe that in those first tiny moments after the Big Bang, random changes in energy could have caused certain areas to grow into new worlds. These regions might still be expanding, drifting far beyond what we can ever see, each one becoming a unique universe, like bubbles in a sea of space. This leads to the idea of a multiverse, a collection of countless universes, all existing side by side, but separated from one another by great distances or even by different dimensions. One especially exciting version of the baby universe theory comes from quantum mechanics, the branch of physics that studies the smallest particles and the strangest behaviors in nature. Famous scientist Stephen Hawking once suggested that black holes, the mysterious objects with gravity so strong that not even light can escape, might actually be doorways to new universes. According to this idea, the center of a black hole, called a singularity, could be a kind of space womb. Instead of just crushing matter into nothingness, it might actually create a new universe on the other side, one with its own stars, galaxies, and maybe even life. From our side, it would look like everything disappeared into the black hole, but from the other side, a brand new universe might be born. As scientists look deeper into these ideas, they are asking some of the biggest questions possible. What is the real nature of dark matter and dark energy? Are they just mistakes in our math? Or do they point to something even deeper, something we haven't found yet? Could baby universes be real? And if so, how many are out there? Each new discovery leads to even more questions, and the more we learn, the more we realize how little we truly know about the universe. Nothing is one of the deepest and most interesting ideas that scientists have ever talked about. Think of a place where there is absolutely nothing. No light, no sound, no air, No time, no space, not even a single bit of dust. That's what nothingness means. The complete lack of anything you can see, touch, feel, or even think of. It's the total opposite of being, which is everything we know: stars, planets, people, thoughts, and feelings. This strange idea, this difference between nothing and something, makes us ask big, important questions about what reality really is. Why is there something instead of nothing? How can anything exist at all? And what does it truly mean to be? Believe it or not, even in science, especially in a field called quantum physics, there's an idea that nothing might not be truly empty. Scientists have found that even the emptiest parts of space are actually full of tiny bits of energy. Little particles can suddenly appear and then disappear again in a moment. These strange happenings show that even what we call a vacuum, or empty space, might be hiding endless possibilities. This means that even when there's no matter and no energy, the chance for creation might still be there, just waiting. It's like the universe is never truly quiet. It's always holding the promise of something new, even in the most still, unseen corners. Thinking about nothingness doesn't just challenge science. It also touches something deep in the human heart. It makes us think about life's worth. If nothing was real, then how amazing is it that something exists at all? How lucky are we to live in a universe filled with stars, planets, water, trees, and even the air we breathe? Life becomes even more special when we realize it could have easily been nothing. Even the tiniest piece in your body, every leaf on a tree, and every star in the sky becomes a wonder. All these things stand out clearly against the quiet, dark background of what could have been. A world without anything. By trying to understand nothingness, we test the limits of what we know. We ask brave questions and look for new ideas. We begin to see that being alive is not just about existing. It's about valuing the ongoing play between what is and what could have never been. Thinkers have been wondering about nothingness for thousands of years. In ancient Greece, more than 2,000 years ago, a man named Parmenides said that nothing couldn't really exist. According to him, even talking about nothing meant you were giving it some kind of being. So for Parmenides, only being was real, and non-being or nothing made no sense. Much later, in the 17th century, a French thinker named René Descartes brought a new way of thinking. He famously said, "I think, therefore I am." What he meant was that if you can doubt or think, then you must exist. His idea showed that the very act of wondering about nothingness proves you are something. So again, we see this strange pull between being and nothing. Jump ahead to the 20th century, and a group of thinkers called existentialists made nothing a main idea. One of the most well-known was Jean-Paul Sartre. He believed that nothingness is closely linked to our human freedom. According to Sartre, life has no set meaning. That can feel scary, but it also gives us a strong duty. Since the universe doesn't give us a purpose, it's up to us to create one. We have to make our own choices, build our own lives, and find meaning even in the face of emptiness. These deep thoughts about nothing haven't stayed only in philosophy books. They've moved into science too, especially in questions about how the universe began. Think about this. If we say the universe came from nothing, what kind of nothing was it? Was it really empty? Or was it filled with strange energy and hidden chances? Some scientists think that even a vacuum, what we once thought was totally empty, is actually filled with something called quantum changes. These are tiny bursts of energy where particles suddenly show up and then vanish. It's as if the universe has a restless energy, even in places that seem completely still. That's why the word nothing can be so tricky. In science, nothing might still be something, after all. If tiny particles can form out of the vacuum, then maybe our entire universe began this way, from a place that looked like nothing but was full of potential. This brings even more questions. If nothing can create something, what rules made that happen? What does it tell us about time, space, and how everything started? These questions don't just belong to science, they touch the core of philosophy too. Different cultures and ways of thinking give different answers. Some say nothing is truly empty. Others say it's just another kind of being. These ideas shape how scientists build theories, how we think about the Big Bang, and even how we see life and death. The idea of nothing makes us look at ourselves and our world in a new way. It's more than just a question. It's a mirror. It shows our curiosity, our fears, and our endless search for meaning. Thinkers like Jean-Paul Sartre and Martin Heidegger, who lived in the 20th century, believed that facing the idea of nothingness can lead to a deep kind of truth. When we remove all our illusions, we're left with the plain fact of being, and in that space, we're free to create, to choose, and to make our lives matter. Even in the vast empty darkness of space, the void is not just absence, it's possibility. It's an open door to everything that might exist. That's why, as strange and unsettling as nothing may seem, it is also one of the most powerful ideas we can ever study. This brings us to the idea of the void. Is nothingness just empty space, a kind of cosmic blank page? Or does it have hidden traits we can't yet see? One well-known thinker, Martin Heidegger, once said that to truly understand what it means to be, we also have to understand what it means not to be. In other words, thinking about nothing helps us make sense of everything. But this also brings another problem. How do we talk about something that isn't there? Our words are all made to describe things that exist, not things that don't. Thinking this way also brings up big questions about purpose. If everything around us appeared suddenly, from nothing, was there a reason behind it? Is there some big plan, or is the universe just a lucky accident? Does life have meaning because we give it meaning, or is there meaning built into the fabric of being? This question, whether the universe has a reason or is just a random event, takes us into deep thought. It's not just an abstract idea. It affects how we see ourselves, our lives, and our futures. It makes us think about whether we are part of a great story, or simply actors on a stage with no script. Many ancient beliefs also have interesting ideas about what came before the beginning. In Eastern thought, especially Hinduism and Buddhism, life is not seen as a straight line but as a circle. In Hindu belief, every person has a soul called Atman, which has lived through many lives. Your past actions, called karma, shape your present and future. Life is a journey through birth, death, and rebirth, moving toward moksha, a kind of spiritual freedom where the soul becomes one with the divine. Buddhism also talks about many lives, but it focuses more on escaping pain. The goal is enlightenment, a deep understanding that sets you free from the cycle of rebirth. In this way, people are encouraged to grow kindness and awareness, to see themselves as part of a greater whole. In contrast, Western thought, especially that shaped by Judaism, Christianity, and ancient Greek and Roman ideas, tends to see life as a straight path. In Christianity, for example, it is believed that God creates each soul at the moment of conception. Life is a one-time experience meant to prepare the soul for eternal life after death. Personal identity is closely tied to moral choices and spiritual destiny, not repeated lives. These different ways of seeing the world, circular versus straight, rebirth versus one life, lead to very different ideas about what it means to exist and what happens before and after life. But both sides ask the same big questions. Who are we? Why are we here? What happens next? Back in the world of modern science, some physicists are also exploring ideas that sound a lot like old philosophy. They talk about the universe starting not from a total absence, but from a quantum vacuum. This isn't nothing, as we usually think of it. It's more like a strange kind of energy-filled emptiness, where tiny particles can pop in and out of existence. According to some ideas, the entire universe may have come from one of these quantum bursts, basically appearing out of almost nothing. This challenges our normal idea of cause and effect. Usually we expect everything to have a reason, like fire coming from a spark. But if the universe just appeared on its own, that clear chain of logic starts to fall apart. It means the rules we live by might not apply to the very beginning of time. This strange thought, that being can come without a cause, has shaken both science and philosophy. It pushes us to think of a universe where even the laws of physics might not be fixed, but instead began along with the universe itself. In the wide world of space science, experts often talk about something called the void. This term doesn't just mean a blank space. It refers to huge parts of the universe where there is almost nothing. No stars, no planets, no gas, not even dust. It's a kind of cosmic emptiness where the lack of matter and energy rules. Strangely enough, this emptiness is not just empty. It plays an important role in how the universe works and grows. This idea of the void is closely linked to what scientists believe the early universe looked like. According to well-known theories, Just after the Big Bang, the universe was filled with energy and light, spread out almost evenly in every direction. At that time, there were no stars, no galaxies, and not even atoms. Matter, as we know it today, had not yet formed. In the very first moments after the universe began, everything was incredibly hot and packed together, tighter than anything we can imagine. It was so dense that even the simplest building blocks of matter, like protons and electrons, could barely exist. Then something extraordinary took place. The universe began to grow. As it expanded, it started to cool down, and little by little, tiny particles began to form and connect with one another. During this time, the spaces between these bits of matter, the empty regions we call the void, also began to grow larger and more noticeable. But this emptiness was not useless or meaningless. It played a very important role in shaping everything that exists today. Gravity, the invisible force that pulls things together, began to draw matter into certain areas. Over long periods of time, this gathering of matter formed stars, galaxies, and the huge cosmic structures that fill the universe. All of these amazing things came into existence within a background of vast, empty space. In a strange and beautiful way, it was the emptiness itself that allowed everything else to take shape. Without the void, there would have been no room for anything to exist at all. The emptiness between stars and galaxies is not just the absence of something, it is part of the design of the universe. Without these open spaces, there would be no stars, no planets, and no galaxies. Scientists continue to study these seemingly empty regions because they hide great mysteries, like dark matter and dark energy. These are strange forms of matter and energy that we cannot see, but they make up almost everything in the universe. Thinking about the void also leads to deeper questions that go beyond science. It makes us wonder how everything began. How did the universe go from a state of nothingness to being full of stars, worlds, and life? What does it really mean for something to exist? And if everything came from nothing, what was that nothing in the first place? Questions like these reach into philosophy and touch on the mystery of existence itself. When we explore the idea of the void, we are not only studying the universe, we are also exploring our own thoughts about existence and creation. We begin to see how the presence of things and the absence of things are both part of reality. This helps us look deeper into where we came from, what the universe truly is, and what our place in it might be. Throughout history, people from every culture have wondered about how the universe began. Long before modern science, ancient civilizations tried to explain creation through myths, legends, and spiritual stories. Many of these stories spoke of gods or powerful forces that brought the universe to life, turning chaos or emptiness into order and beauty. The birth of stars or worlds often symbolized renewal and hope, a reminder that life can arise even after darkness or destruction. In a way, modern science tells a similar story, but in its own language. When a massive star reaches the end of its life, it explodes in a powerful event known as a supernova. At first glance, this might look like pure destruction, but it is actually the beginning of something new. That explosion scatters important elements like carbon, iron, and oxygen across space, the same elements that later form new stars, planets, and even living beings. In the universe, every ending gives rise to a new beginning. This constant cycle of destruction and creation is part of how the universe keeps changing and growing. The Big Bang, believed to have happened about 13,800,000,000 years ago, was the great beginning of everything we know. And even the possible future of the universe, whether it will one day collapse in on itself or continue expanding forever, reminds us of the endless rhythm of birth, death, and renewal. Scientists once thought that time and space were fixed and never changed. This way of thinking, called classical physics, reached its height with the famous scientist Sir Isaac Newton. According to Newton, time moved forward at the same steady pace for everyone, no matter how fast they were going or where they were. He also saw space as a huge, still stage where everything happened, like a theatre that stayed the same while the actors, planets, stars, and people moved around on it. This idea worked well for many things, especially for what we see every day, like falling apples or moving trains. But as science advanced and the 20th century came closer, people started to see that Newton's rules didn't work very well when things moved extremely fast, close to the speed of light, or when gravity was very strong. Then came a man named Albert Einstein, who changed everything. In the year 1905, he introduced something called the theory of special relativity. It was a completely new way of seeing the universe. Einstein said that space and time were not two separate things. They were actually part of one single whole called spacetime. This meant that time didn't move the same for everyone. How fast or slow time passed could depend on how fast someone was moving. For example, someone travelling in a spaceship near the speed of light would actually age more slowly than someone who stayed on Earth. This strange idea was shown in a famous thought experiment about two twins. One goes on a space trip at high speed, while the other stays home. When the travelling twin returns, they are younger than their sibling. Einstein didn't stop there. In the year 1915, he introduced another big idea called general relativity. This built on his earlier theory and added gravity. He explained that heavy things, like planets, stars, and black holes, actually bend the fabric of space-time around them. This bending changes how time passes and how light moves. For example, time moves a little slower near Earth's surface, where gravity is stronger than it does far out in space. Scientists have tested this with very precise atomic clocks, and it turned out to be true. The change from classical physics to modern physics completely transformed how we see the universe. Space was no longer just an empty box, and time was no longer a single clock ticking the same for everyone. Instead, space and time became living parts of the universe, always connected and always changing depending on motion and gravity. Einstein's discoveries didn't just help us understand the universe, they also led to real inventions. For example, technologies like GPS, Global Positioning System, which help you find your way with a phone or a car, depend on Einstein's ideas. Without adjusting for the way time flows differently for satellites in orbit, GPS would give wrong results. But Einstein's theory also opened the door to even deeper questions, especially about the beginning of everything, the Big Bang. Scientists once thought of time as a straight line, where events happened one after another, starting from a clear beginning. But now, new ideas are challenging that simple view. Some scientists talk about nonlinear time. This means time might not flow in a straight line at all. Instead, events could be connected in strange ways, looping back or even happening out of order. It's possible that the past, present and future could affect each other all at once, in ways we still don't fully understand. This idea becomes especially interesting when we think about what happened before the Big Bang. If the universe began with a huge explosion from a tiny dense point, what scientists call a singularity, then maybe time itself didn't even exist before that moment. Or maybe time existed in a very different way, like a shifting web instead of a straight path. In this way of thinking, the beginning of the universe wasn't just a starting point, but more like a change or transformation. Some theories even say there could be many universes, or that the universe goes through cycles, with no true beginning or end, only endless change. This also changes how we think about cause and effect. If time isn't strictly straight, then the future might affect the past just as the past affects the future. It's a wild idea, but it helps scientists and thinkers ask new questions about what existence really means. When we look deep into space, or into black holes, where gravity is extremely strong, our normal ideas about time start to break down. Time might stretch, twist, or even stop completely in these extreme places. That's why a nonlinear idea of time might help explain what's happening, where the usual rules no longer work. The ideas behind relativity go far beyond just physics and math. They touch some of the deepest questions we can ask about the universe. They make us think about where everything came from, what life and existence really mean, and what reality itself truly is. One of the most puzzling questions is whether time can exist on its own, without space. This is not a simple idea. It goes right to the heart of how we understand the universe. In everyday life, we think of time and space as separate things. But in the early 20th century, a brilliant scientist named Albert Einstein changed that view forever with his theory of general relativity. According to this theory, time and space are not different things. They are parts of a single, joined whole called spacetime. This spacetime is like a four-dimensional fabric that makes up the very structure of the universe. There are 3 dimensions of space: length, width, and height, and time is the fourth. In this view, time is closely connected to space. You can't change one without changing the other. However, not all theories agree with this. In some versions of quantum physics, time might be something more basic than space. Some scientists have even asked, What if time existed before space? What if time was already moving before the universe began? This strange but exciting idea leads us into the mystery of how the universe began. If time already existed before space, it might mean that things were already happening, even before the Big Bang. The Big Bang is the name for the moment when everything in our universe began. According to this theory, the universe started about 13.8 billion years ago, when all space, time, matter, and energy burst into being from an unimaginably hot and dense point. That moment marked the start of both time and space as we know them. But what if something came before it? What if time stretched back beyond that moment? That would mean reality is far more mysterious than we ever thought. It could mean that cause and effect, where one thing leads to another, might not have worked the same way back then. Trying to picture such a reality is very hard for us, since we live in a world where time always moves forward and space surrounds us. Still, thinking about these big ideas helps us better understand how everything began. Can we even imagine time without space? What does time mean when there are no stars, no planets, not even empty space, just something else? These questions are like windows into the unknown, pushing the limits of science and philosophy. They make us wonder not just how the universe began, but why it began, and what it really means to exist. The Big Bang Theory tells us that about 13.8 billion years ago, the universe began in a sudden burst of heat, light, and energy. But it wasn't just matter and energy that were born in that instant. Time and space themselves came into being. Before that, our normal ideas of before and after didn't make sense because time as we know it didn't exist yet. Everything we know, space, time, stars, galaxies, even the atoms in our bodies, came from that first moment. As the universe expanded, it began to cool down. During that cooling, tiny particles started to form. Those particles then joined together to make atoms. Over billions of years, those atoms gathered into stars and galaxies. In this way, the flow of time became linked to the growth and change of the universe. Time became like a thread running through everything, from the smallest particles to the biggest galaxies. Every moment in the universe's story became part of this unfolding cosmic journey. Albert Einstein's theory of general relativity also tells us something even more amazing. It says that mass and energy can bend the fabric of spacetime. That means objects like stars and planets can curve space and slow down time. So when the universe expands, it isn't just matter moving through space, it's space itself that is stretching. And because time is part of space, time stretches too. It's as if the whole universe is a giant balloon that keeps growing, and time is part of the rubber that makes it up. Scientists have also studied what quantum physics says about the beginning of the universe. Quantum physics is the science of the very small, the strange, unpredictable world of particles and energy. Some theories say that tiny random changes in energy, called quantum fluctuations, might have started the Big Bang. This leads to bold and exciting ideas, like the possibility that our universe is just one of many, a small part of a much larger multiverse, where countless other universes might also exist. If these ideas are true, then the Big Bang wasn't just the start of our universe. It might have been one event in an endless chain of cosmic happenings. This makes us ask even deeper questions. What is reality? Is time something that lasts forever, or did it truly begin with the Big Bang? Could there be other kinds of time, or even places where time moves differently? Time plays a huge role in how we understand the universe. When we look at faraway galaxies, we're also looking into the past. Because light takes time to travel, we see those galaxies as they were billions of years ago. This means time acts like a cosmic time machine, showing us what the universe looked like long ago. Scientists use this light to measure how fast the universe is growing. This is called Hubble's law, and it shows that the farther away a galaxy is, the faster it is moving away from us. By studying this growth, scientists can find out how old the universe is. They look at how much the light from faraway galaxies has stretched, a process called redshift, to measure how long the universe has been expanding. This helps them learn how stars, galaxies, and planets have formed over billions of years. The light we see today from the most distant galaxies began its journey billions of years ago, giving us a look into the ancient past. Einstein's theory of relativity also changed how we see time itself. It showed that time does not pass the same for everyone. Time can move slower near something with a lot of gravity, like a black hole, or for someone travelling very fast, close to the speed of light. This means time is not fixed. It can bend, stretch, and twist, depending on where you are and how fast you move. Because of this, understanding how the universe expands becomes more difficult. Time might act differently in different parts of the universe. Loop quantum gravity gives a new and brave way to think about the universe, especially when we wonder what might have happened before the Big Bang. This idea doesn't just add to what we already know, it dares to question the very base of how we understand space and time. For a long time, scientists thought of space and time as smooth and unbroken, like a calm sheet that spreads endlessly in all directions. But loop quantum gravity suggests something very different. Instead of being one smooth flow, space and time might actually be made of tiny separate parts, almost like the small threads of a huge cosmic cloth. Imagine that instead of being smooth and whole, space is built from countless little loops, each one turning and linking with others, forming a huge unseen web that holds the universe together. These loops are incredibly small, much smaller than anything we can see, but together they make the basic structure of everything that exists. Now let's go back in our imagination, not just millions or billions of years, but to the very beginning of time itself. Most people know about the Big Bang theory, which says the universe began about 13.8 billion years ago with a huge explosion from a single point, called a singularity. But loop quantum gravity tells a different, more mysterious story. According to this idea, there might never have been a singularity at all. Instead, what we call the Big Bang could have been a kind of bounce, a change from an earlier state of the universe. In other words, before our universe began to expand, there might have been another universe collapsing into itself, and when that universe reached a certain point, it didn't end, it bounced, giving birth to our universe. This suggests something truly amazing. Time might not be a straight line with a start and an end. It could be more like a circle, with no clear beginning or finish, just endless cycles of birth, death, and rebirth on a cosmic scale. In this view, the universe doesn't just begin once and move forward forever. It changes again and again, shaped by deep and complex quantum processes. Near the moment of the Big Bang, when everything was squeezed into a state of unbelievable thickness, the normal laws of physics stop working. Gravity no longer acts the way we expect, space and time start to blur. In these extreme conditions, loop quantum gravity lets us imagine a world where the universe doesn't just come from nothing, but from something else, something ruled by the strange and powerful laws of quantum gravity. This idea also changes how we think about existence itself. If space and time are made of tiny bits, if they're quantized, as scientists say, then everything we know, from galaxies to particles, rests on a structure far more detailed and mysterious than we ever thought. It means we may need to rethink not only the beginning of the universe, but the very fabric of reality. The questions raised by loop quantum gravity aren't just scientific, they're deeply thoughtful too. People have long wondered about time. Some see it as a river that flows from the past through the present into the future. Others, like the great thinker Immanuel Kant, believe that time might actually live inside our minds, a way for our brains to understand the world around us. This brings up some fascinating questions. Does time exist on its own, out there in the universe? Or is it something we create in our minds as we try to understand our place in the cosmos? Science and philosophy meet at this point. The question of what happened before the Big Bang connects directly to our deepest ideas about what time really is. According to the usual scientific view, time began with the Big Bang about 13.8 billion years ago. So when we ask what came before that, we're asking something that may not even make sense in the normal way. If there was no time before the Big Bang, then before might not exist at all. But some scientists think there might be more to the story. New ideas, like loop quantum gravity, quantum cosmology, and the idea of a multiverse, suggest that our universe might be just one of many, or that time might act in strange, non-straight ways we can hardly imagine. All of this brings us back to a question as old as humanity itself. Can we ever truly understand the beginning of everything? Or are our minds simply not made to grasp such huge and complex truths? As scientists study the universe's first moments using math and advanced tools, philosophers keep exploring the same questions through deep thought and reflection. astronomers have found an amazing way to look back into the very old past of our universe. They do this by studying a weak glow that fills all of space, known as the cosmic microwave background radiation, often called the afterglow of the Big Bang. This light is the oldest we can see, and has been travelling through space for over 13 billion years. It first appeared about 380,000 years after the universe began, when it finally cooled enough for atoms to form and for light, called photons, to move freely through space. To find this extremely old and faint light, scientists use very sensitive tools. These include special telescopes and satellites that can detect microwave radiation, a type of light that our eyes cannot see. One of the most important projects in this area was the Wilkinson Microwave Anisotropy Probe, or WMAP for short. This satellite made a map showing tiny changes in the temperature of the cosmic microwave background across the whole sky. These very small differences, just millionths of a degree, gave scientists clues about how matter was spread out in the early universe. Later, an even stronger mission called the Planck satellite was launched. It gave scientists the most detailed map ever made of this ancient light. Planck helped improve our understanding of the universe's shape, what it is made of, and even how old it is. Thanks to this information, we now know that the universe is about 13,800,000,000 years old, and is mostly flat, not curved. To avoid problems from Earth's atmosphere, which can block or change microwave signals, these studies are usually done in space or from very high places on Earth. The tools used in these missions are very sensitive. They can notice tiny changes in temperature and in the way light waves move, called polarization. By studying these details, scientists can learn about the early conditions of the universe and how it has changed and grown since then. These studies have not only confirmed that the universe is flat, but also given strong proof for mysterious things called dark matter and dark energy. Studying the cosmic microwave background has helped astronomers map the large structure of the universe, showing how galaxies and clusters of galaxies formed over billions of years. Every bit of this ancient light tells a story about the universe's journey from a hot, dense beginning to the huge, star-filled space we see today. Another powerful way scientists explore the universe's past and present is by listening to the universe. Not with sound, but with ripples in space and time called gravitational waves. These waves are created during some of the most powerful and energetic events in space, such as when black holes or neutron stars crash into each other. To detect them, scientists built a special observatory called the Laser Interferometer Gravitational Wave Observatory, or LIGO. LIGO has two sites, one in Washington State and the other in Louisiana, each with long tunnels about 4 kilometers long. Inside these tunnels, laser beams bounce between mirrors that are very carefully hung. When a gravitational wave passes through, it slightly changes the distance between the mirrors by less than the width of a proton. But these tiny changes are enough for LIGO's instruments to notice. Finding gravitational waves is not just an amazing achievement, it's like opening a new window into cosmic events we could never see with light alone. These waves carry information about where they came from, how heavy the black holes were, how fast they were spinning, and how they collided. This helps scientists learn more about how stars live and die, what happens in the most extreme places, and even test the deepest laws of physics. Even though LIGO mostly finds waves from events happening in today's universe, its discoveries also help us understand the very early moments after the Big Bang. Some theories suggest that the early universe, especially during a fast-growing phase called cosmic inflation, might have made strong gravitational waves. Even though we haven't yet found these early waves directly, studying the ones we can detect helps improve our ideas about how the universe was born and how its first structures formed. LIGO's success has started a whole new branch of science called gravitational wave astronomy. This growing field combines the power of gravitational waves with regular telescope observations, creating what scientists call a multi-messenger approach. By putting together these different messages from the universe, we get a richer and more complete picture of how it works, from its earliest beginnings to the amazing events still happening today. Another incredible tool for exploring the early universe is the James Webb Space Telescope. Unlike normal telescopes that mostly see visible light, the James Webb is built to detect infrared light. This kind of light is perfect for finding faraway galaxies and stars that formed billions of years ago. When light travels through space for such a long time, it gets stretched by the universe's expansion. This stretching, called redshift, moves the light into the infrared range. Many of the first stars and galaxies were born during a time scientists call the cosmic dawn, which happened just a few 100 million years after the Big Bang. The light from these young objects has been travelling through space ever since, and it has been stretched so much that only a telescope like the James Webb can see it. By capturing this weak infrared light, the James Webb Space Telescope lets astronomers look farther back in time than ever before. This telescope doesn't just take beautiful pictures, it studies the light it gathers to find out what these ancient galaxies are made of, how hot they are, how fast they're moving, and how they've changed over time. For example, by looking at how galaxies grouped together and grew larger, scientists can better understand how the universe built its huge structures. The James Webb also helps us study how elements were formed in the early universe. Right after the Big Bang, only the lightest elements, like hydrogen and helium, existed. Heavier elements were made later inside stars. By studying light from ancient stars and galaxies, scientists can learn when and how these elements formed, adding another piece to the story of how the universe became what it is today. In many ways, the James Webb Space Telescope is like a time machine. It lets us look deep into the past, showing a clearer picture of how everything began and how it has changed over billions of years. When combined with data from the cosmic microwave background, gravitational waves, and other telescopes, we are slowly putting together the full, amazing story of the universe, from its fiery start to its mysterious present and ever-changing future. When we look deep into space, we notice something interesting called redshift. This happens when light from faraway objects like galaxies gets stretched to longer wavelengths as it moves through the universe. Think of light as a wave. When something moves away from us, those waves get pulled longer, pushing the light toward the red end of the spectrum. That's why it's called redshift. It's like when a train whistle drops in pitch as the train moves away. The sound stretches out, just like light does in space. The farther away a galaxy is, the more its light is redshifted. This stretching tells astronomers how fast the galaxy is moving away from us. That might sound simple, but it's actually one of the strongest tools we have to understand the universe. By measuring how much redshift we see in a galaxy's light, we can find out its speed and distance, giving us clues about how fast the universe is expanding. This idea became clear in the early part of the 20th century, when a scientist named Edwin Hubble saw that the farther away a galaxy is, the faster it moves away. That discovery became the foundation of modern cosmology. But redshift tells us even more than that. It helps us guess the age of the universe. As light from old galaxies travels billions of years to reach us, it carries a kind of time capsule with it. The more redshifted the light is, the older and farther away the galaxy must be. This means scientists can build a timeline of the universe's story by studying how stretched this old light has become. Redshift also helps us understand something even more mysterious: dark energy. This strange force seems to be speeding up the universe's growth. By looking at the redshift of light from galaxies at different distances, scientists can see how the speed of expansion has changed over time. That gives us a clearer view not just of the past, but of what the future might bring. In a way, redshift lets us follow the universe's whole life story, from its explosive start to the vast, dark future ahead. Now let's move from light to something even harder to catch: gravitational waves. These are tiny ripples in the fabric of space and time made by huge cosmic events. Some of the oldest ones come from just moments after the Big Bang, during a time called cosmic inflation. But these signals are extremely faint and can be covered up by other space noise. That's why scientists need very advanced tools to find them. One such tool is LIGO, the Laser Interferometer Gravitational Wave Observatory. It listens for tiny changes in space and time, caused by things like joining black holes. But future observatories, like the space-based LISA and the upcoming LIGO Australia, hope to find even older signals from the early universe itself. These observatories will be so sensitive they can catch the faint whispers of the universe's birth. Another way scientists look for ancient gravitational waves is through the cosmic microwave background, or CMB. This is the faint glow left over from the Big Bang, like the dying embers of a cosmic fire. Tiny patterns in the CMB's light, especially something called B modes, might hold the signs of those early gravitational waves. With new telescopes like the Simons Observatory and past missions like Planck, scientists are studying these small clues in the CMB to learn more about the start of everything. Gravitational waves also help test different models of inflation, those ideas that try to explain what happened in the first split seconds after the Big Bang. By matching what we see to what we expect, researchers can tell which ideas make sense and which don't. This not only teaches us about gravitational waves, but also about the deep laws of nature and what shaped the universe at the very beginning. Another amazing tool we use to study the early universe is the Large Hadron Collider, or LHC. This huge machine, located near Geneva in Switzerland, is the world's biggest and most powerful particle accelerator. It's about 17 miles around and crashes protons together at nearly the speed of light. Why do scientists do this? Because those crashes bring back the high-energy conditions that existed right after the Big Bang. One of the LHC's most important finds was the Higgs boson in the year 2012. This special particle helps explain why things have weight. Finding it proved a huge piece of the puzzle about how the universe works. The LHC also lets scientists study a strange state of matter called quark-gluon plasma, a kind of super-hot soup of the tiny pieces that make up atoms. This rare state may have lasted for just a few millionths of a second after the Big Bang. Studying it helps us understand how the universe cooled down and formed the matter we see today. Now let's turn to something even harder to find: neutrinos. These are tiny particles that barely react with anything. They're sometimes called ghost particles because they can pass through whole planets without touching anything, but they're very important. Neutrino detectors, like IceCube in Antarctica and Super Kamiokande in Japan, can catch high-energy neutrinos from space, especially from things like exploding stars called supernovae. Neutrinos were made in huge numbers just moments after the Big Bang. Although we can't see the very first ones directly, modern detectors can catch newer neutrinos that help us understand those early times. For example, when a supernova explodes, it sends out a flood of neutrinos. By studying those, scientists learn about how stars work inside and how elements were formed. Neutrinos also played a big part in nucleosynthesis, the making of light elements like hydrogen and helium. By understanding how neutrinos affected those early reactions, scientists can fine-tune their models of how the universe's first atoms formed. One of the most exciting neutrino projects today is called DUNE, the Deep Underground Neutrino Experiment. It's being built deep underground in South Dakota and will use a strong beam of neutrinos from a lab in Illinois. DUNE hopes to solve puzzles about how neutrinos change from one type to another, a process called oscillation. This could help answer a huge question in science. Why does the universe have more matter than antimatter? DUNE will also look for neutrinos from future supernovae and try to find out if there's a link between neutrinos and dark matter. This experiment could change what we know about both tiny particles and the universe as a whole. Another way scientists study the faraway universe is by watching quasars. These are extremely bright objects powered by giant black holes at the centers of distant galaxies. Quasars are so bright they can shine brighter than whole galaxies and be seen across billions of light years. As their light travels to Earth, it passes through clouds of gas and dust, picking up clues along the way. By studying this light, astronomers can learn about the stuff that filled the universe long ago. Quasars also help scientists understand how galaxies and black holes grew over time. Their brightness lets us look deep into the past. Changes in quasar behavior over time show how star-making and galaxy growth have changed. When quasars shoot out energy in the form of winds and jets, they can even affect how stars form in their home galaxies, a process called feedback. Studying quasars gives us a rich view of the early universe, from its materials to its shape and growth. As technology moves forward, new tools are giving us clearer and deeper views of the cosmos. The James Webb Space Telescope, launched not long ago, is already changing how we see faraway galaxies and stars. Future telescopes will look at different kinds of signals, like gravitational waves or rare types of light, helping us explore more parts of the early universe. Imagine the universe as a tiny dot, smaller than an atom, smaller than anything we can see or even imagine. According to an amazing idea called cosmic inflation, something extraordinary happened during the very first moment of existence. In less than a trillionth of a second after the Big Bang, the universe went through an unbelievable growth spurt. It didn't just grow, it exploded in size, expanding faster than the speed of light itself. This sudden event, known as inflation, happened in the tiniest bit of time right at the start, within the first millionth of a billionth of a billionth of a second. This idea helps scientists solve some deep and puzzling mysteries about our universe. For example, why does the universe look almost the same no matter which way we look? Why is the leftover heat from the Big Bang, the cosmic microwave background, so evenly spread out across the sky? And why does the universe seem so flat and balanced instead of curved or messy? Inflation gives answers. It says that even though the universe began very small and possibly messy, it quickly smoothed itself out during this super-fast growth. Energy spread more evenly, setting the stage for the birth of galaxies, stars, and everything we see today. The idea of cosmic inflation was first introduced in the early 1980s by an American scientist named Alan Guth. Guth suggested that in the very first moments of the universe, a mysterious high-energy force made space expand at an unimaginable speed. This force overpowered everything else and worked like a balloon pump, stretching the universe faster than light itself. Guth's idea helped explain why the universe is so smooth, flat, and finely balanced. After Guth shared his idea, other great thinkers added their own thoughts. Scientists like Andre Linde and Paul Steinhardt developed different versions of inflation. They studied how inflation might start, how it might end, and what could power it. Thanks to their work, cosmic inflation became a strong and flexible theory that fits well into cosmology, the study of how the universe began, how it works, and where it's going. One of the most exciting parts of this theory is that inflation might not be over. It's possible that it's still happening, but much more slowly and gently. Some versions of the theory even suggest that inflation could be creating new universes beyond our own, each with its own laws of nature, a mind-blowing idea called the multiverse. Inflation solves two big puzzles about the universe, the horizon problem and the flatness problem. The horizon problem is this: when we look far into space in opposite directions, everything looks almost the same, even though those areas are so far apart that light hasn't had time to travel between them since the universe began. How could they possibly have shared the same temperature? Inflation solves this by saying that all parts of the universe were once very close together and could mix and even out before being blown apart during the rapid expansion. That's why we now see the same temperature and structure even across huge distances. The flatness problem is another mystery. According to Einstein's theory of general relativity, the shape of the universe depends on how much matter and energy it has. If it were too dense, it would curve inward like a ball. If it weren't dense enough, it would curve outward like a saddle. But when scientists measure the universe, they find it is almost perfectly flat. Inflation explains this by saying that the huge stretching during inflation would have flattened any curve in space, just like how a small bump on a balloon becomes barely visible when the balloon is blown up large enough. So the universe looks flat because inflation smoothed out all its curves. Inflation also helps explain how galaxies and stars first formed. During inflation, tiny quantum ripples called quantum fluctuations appeared in the energy field that caused the expansion. These tiny ripples were like little seeds. When inflation ended and the universe cooled, those small seeds grew into areas with slightly more matter, which gravity pulled together to form galaxies, stars, and the vast web of structures we see today. Without inflation, there would be no clear reason for where these tiny but important differences came from. The idea of cosmic inflation isn't just a clever guess. It's supported by real evidence. One major piece of proof comes from the cosmic microwave background radiation, a faint glow left from the Big Bang. Satellites like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck spacecraft have measured tiny temperature differences in this glow. These patterns match exactly what inflation predicts. They show that small ripples in density, caused by quantum effects during inflation, were real and helped shape the universe. Another key piece of evidence is the large-scale structure of the universe itself. When scientists map the positions of galaxies, they find that galaxies are not scattered randomly. Instead, they form a kind of cosmic web with clusters, strands, and huge empty spaces called voids. These patterns also match what inflation predicts. The tiny quantum ripples, stretched and strengthened by inflation, left behind marks that guided the growth of galaxies over billions of years. There's one more sign scientists are still searching for: gravitational waves from the time of inflation. These are ripples in space itself that would have been made by the violent stretching of the universe. If scientists can find these ancient waves, it would be like hearing the echo of inflation itself. So far, these waves haven't been found, but powerful new observatories are looking for them, and finding them would be a huge step forward. The idea of cosmic inflation is not just important for explaining how our universe began, it also leads to some truly amazing possibilities. One of the most exciting is the idea of the multiverse. This is the belief that our universe is just one of many, maybe millions or even billions of others, each with its own rules of nature, its own particles, and maybe even its own kind of space and time. Cosmic inflation tells us that, in the earliest moments after the Big Bang, the universe didn't just grow, it exploded in size at an incredible rate. This expansion happened very fast, in less than a trillionth of a second. But here's the exciting part. Inflation might not have happened the same way everywhere. Some places may have expanded slower, others faster, and some may still be expanding even now. This leads to a bold and thrilling idea called eternal inflation. According to this idea, inflation never fully stops. In some parts of the larger universe, inflation slows and ends, and those areas become finished universes, like ours. But in other places, inflation keeps going forever. This means new universes can keep forming, like bubbles rising in a pot of boiling water. These are called bubble universes or pocket universes. Each bubble universe would be like a separate reality, with its own version of physics. Some might have stronger gravity, others might have no atoms at all, and some might be completely dark or made of different types of matter. The result is a huge cosmic landscape filled with an unimaginable number of universes, each with its own story. One reason scientists take this idea seriously is because of something called fine-tuning. Our universe seems to be perfectly set up for life. The strength of gravity, the charge of an electron, the expansion speed of the universe, all these values are so exact that even tiny changes could make life impossible. But if there are countless universes, each with different properties, then it's not surprising that one of them, ours, just happens to have the right conditions for life. In this way, the multiverse gives a natural explanation for why our universe is so friendly to life, without needing to assume that it was specially made. Still, the multiverse is very controversial. It's an exciting idea, but it's also hard to test. Scientists like ideas they can observe or measure, and right now, there's no direct way to look into these other universes or prove they exist. So, while inflation is a strong idea supported by evidence, the multiverse is still in the area of theory and guesswork. But as our tools and understanding improve, this research might reveal new truths about the nature of everything. To explain how inflation works, scientists came up with a theoretical idea called the Inflaton field. This is not something we can see or touch, but it's thought to have filled all of space in the very early universe. This Inflaton field carried a strange kind of energy that did not act like normal matter or light. Instead of shining or turning into particles, it created a kind of pushing pressure, a force that spread space apart incredibly fast. You can imagine this energy as an invisible pressure cooker, stretching space like dough being pulled from every side. This is what made the universe grow so fast in such a short time. This growth wasn't just fast, it was exponential, meaning it doubled in size again and again in the blink of an eye. Eventually, the Inflaton field ran out of energy. When that happened, it began to break down into particles, giving off heat and radiation. This moment is called reheating, and it marked the end of inflation. From this point on, the universe was filled with hot particles, light and energy, the perfect ingredients for forming atoms, stars and galaxies. This was the start of the universe as we know it. Scientists are still trying to figure out exactly what the Inflaton field is, what kind of particle it might involve, and how it interacts with other forces in nature. There are many versions of inflation theory, each with its own model of the Inflaton field. If we could ever find solid proof for it, such as tiny patterns in the sky or subtle signals in cosmic radiation, it would be a big step forward in understanding our origins. One of the biggest mysteries inflation helps solve is why the cosmic microwave background radiation, the faint afterglow of the Big Bang, looks so even and smooth. When we look at this radiation, we see that it has almost exactly the same temperature everywhere in the sky, with only tiny little bumps or ripples. But here's the question. How did all these faraway parts of the universe get to be the same temperature if they've never had time to interact? Inflation gives us the answer. In the earliest moments of the universe before inflation happened, all regions were close together and could easily share heat and energy. Then, during inflation, space expanded so fast that those once close areas were ripped far apart, faster than the speed of light could travel. This means they had already agreed on a temperature before being separated, explaining why the sky looks so uniform today. But inflation didn't erase everything. Tiny random changes, caused by quantum jitters during inflation, got stretched across the universe. These small differences became the seeds for galaxies and stars. Over billions of years, gravity pulled matter into these denser spots, eventually forming the cosmic structures we see today. Over time, scientists have developed several ideas to explain how the universe suddenly expanded in its earliest moments. This dramatic growth is called cosmic inflation, and different models try to describe what caused it and how it happened. These models mainly differ in how they describe the Inflaton field, the mysterious force thought to have powered this rapid growth. One of the first and simplest ideas is called the new inflation model. According to this model, the Inflaton field started out in what is called a metastable state, like a ball resting in a shallow dip on a hill, not yet at the bottom. While in this state it had a lot of energy, and as the field began to roll down to a lower energy level, like the ball finally rolling to the bottom, it released energy. This sudden release made the universe expand rapidly. Once the Inflaton field reached its lowest energy state, inflation ended. After that, the energy turned into particles and light in a stage called reheating, setting the stage for the formation of atoms, stars, and galaxies. Another important idea is the chaotic inflation model. This one suggests that inflation could start under many different starting conditions. In this model, the Inflaton field doesn't need to begin in a special state. It could start with very high energy, like a ball sitting high on a steep hill, and still cause inflation. This model allows the Inflaton field to take many different shapes, such as simple curves like parabolas or steeper ones. Because of this flexibility, inflation could happen in many ways, leading to all kinds of possible universes. This idea helps explain why our universe looks the way it does, even if it started from random conditions. Then there's an even more mind-blowing idea called eternal inflation. This model takes chaotic inflation further. It suggests that, in some parts of space, inflation never really stops. While some parts of the universe stop inflating and become bubble-like regions, each forming its own universe, other parts keep expanding forever. This leads to the amazing idea of a multiverse, a huge cosmic landscape filled with countless universes, each possibly having different laws of physics, particles, or even dimensions. According to this idea, our universe is just one bubble among many, all born from an endless process of inflation. Yet another fascinating model is called natural inflation. This one uses ideas from particle physics, especially a type of particle called an axion, which is still theoretical but might help explain some of the deepest puzzles in physics. In this model, the axion field acts as the inflaton. What makes this idea interesting is that it connects the birth of the universe with the world of tiny particles, linking cosmology with the very smallest building blocks of nature. If true, it could help bring together our understanding of the universe on both cosmic and quantum levels. Each of these models shows different parts of how inflation may have worked. Scientists compare these ideas with real observations, especially the faint glow left behind from the Big Bang, known as the cosmic microwave background. This ancient light carries clues from over 13 billion years ago. By studying it carefully, researchers hope to figure out which inflation model, if any, best matches reality. The theory of cosmic inflation has changed our understanding of just how huge and old the universe might be. Before inflation was suggested, it was hard to explain why the universe looks so uniform in every direction. Without inflation, parts of space might never have had the chance to interact with each other. But if the universe expanded extremely fast in the first tiny fraction of a second after the Big Bang, so fast that it doubled in size many times, then even parts of the cosmos that are now incredibly far apart were once close together. This solves the puzzle of the universe's smoothness, and suggests that the real universe is much larger than what we can currently see. Inflation also helps us better estimate the age of the universe. By studying features in the cosmic microwave background and the structure of galaxies on a huge scale, scientists can work backwards to figure out how much time has passed since the universe began. While the inflation period itself lasted just a tiny fraction of a second, less than 1/1,000,000,000th of a second, it set the stage for everything that followed. After inflation ended, the universe continued to expand more slowly, developing into the complex cosmos we see today. With inflation included in the timeline, scientists can more accurately estimate that the universe is about 13.8 billion years old. Another important idea in this story is redshift, the stretching of light waves as galaxies move away from us. The faster a galaxy moves away, the more its light shifts toward the red end of the spectrum. This redshift tells us about how fast the universe is growing. By understanding how inflation affected that growth, scientists can better understand these redshifts and learn how the universe's expansion has changed over time. This helps create a clearer map of both the universe's age and its size. One of the most exciting predictions of inflation is the chance of primordial gravitational waves, tiny ripples in the fabric of space and time itself. These waves are thought to have formed during inflation, caused by quantum fluctuations and the extreme stretching of space. Unlike light, gravitational waves can pass through matter almost completely untouched. This means they carry information from the very start of the universe. In many inflation models, these gravitational waves show up as tensor fluctuations, tiny changes in the shape of space. These are different from scalar fluctuations, which are changes in density and are responsible for the large structures like galaxies that we see today. Detecting these primordial gravitational waves would be a big breakthrough. It would give direct proof that inflation really happened and provide clues about the huge amount of energy involved at that time. To find these waves, scientists look at the cosmic microwave background again. They search for a specific pattern of polarization called B-mode polarization, a subtle swirling pattern in the light caused by gravitational waves moving through space. So far, these patterns haven't been confirmed, but experiments are ongoing. Projects like the Laser Interferometer Gravitational Wave Observatory and future missions like the Laser Interferometer Space Antenna are built to search for these ancient waves. If they succeed, it could open a new window into the universe's earliest moments and reveal completely new parts of physics. In the coming years, many more experiments will try to test the theory of inflation in different ways. One of the most promising efforts is studying the cosmic microwave background in even greater detail. Advanced observatories like the Simons Observatory and the CMBS-4 project are being built to find the tiniest fluctuations and polarization signals left by inflation. At the same time, large surveys of galaxies, like those planned with the Vera C. Rubin Observatory, will map the positions and movements of billions of galaxies. These maps can be compared with predictions made by inflation models. If something doesn't match, it could point scientists toward new or improved theories. Another exciting path involves particle physics. Powerful machines like the Large Hadron Collider might find new particles that could be connected to the Inflaton field. If we can find signs of such particles, it might link the story of inflation directly to the rules of quantum physics, helping to connect our understanding of the very large and the very small. When we think about the beginnings of the universe, we often picture an empty space before anything existed. But modern science tells a very different story, one that challenges what we think we know about reality. Instead of a cold, lifeless emptiness, what we once called empty space is actually a hidden, active place full of energy and strange activity. This brings us into the fascinating world of quantum physics, the part of science that studies how the universe works at the smallest levels. At the heart of quantum physics is a surprising discovery. Space, even when it has no matter or light, is never truly empty. Instead, it is full of what scientists call quantum fluctuations, tiny, unpredictable bursts of energy that appear and disappear in an instant. These fluctuations are not just random events, they are the foundation of some of the most amazing discoveries in modern science. They might even hold the answer to one of the biggest mysteries. How did the universe begin? For thousands of years, people believed that if you removed everything from a space, every atom, every particle, every bit of light, you would be left with true emptiness. This idea of nothingness was widely accepted by scientists and thinkers, but discoveries in quantum physics over the past 100 years have completely overturned this belief. In reality, what looks like empty space is far from empty. Instead, it is a restless sea of energy, always moving and changing because of quantum fluctuations. These fluctuations happen because of something called the uncertainty principle, an important idea in quantum physics introduced by the scientist Werner Heisenberg. This principle says that at the most basic level, we can never know both the exact position and the exact speed of a particle at the same time. This unavoidable uncertainty leads to a strange result. Even in what we see as a vacuum, energy constantly flickers in and out of existence. This restless and unpredictable activity creates what scientists call quantum foam, an unseen, churning sea of energy at the tiniest levels of reality. Even though we cannot see it with our eyes, its effects can be measured and have been proven through experiments. The first strong evidence that empty space contains energy came in the year 1947, thanks to two Dutch scientists named Hendrik Casimir and Dirk Polder. They carried out a simple but groundbreaking experiment that revealed one of the strangest forces in the universe, now called the Casimir effect. In their experiment, Casimir and Polder placed two small, flat metal plates very close together inside a vacuum, a place where, according to classical physics, there should be nothing at all. If space were truly empty, nothing should have happened. But to their surprise, the plates moved toward each other, as if an invisible force was pulling them together. At first, this seemed impossible. What could be causing this strange pull between the plates? The answer lay in the quantum fluctuations of space itself. Even in a vacuum, energy fluctuations happen all around the plates, but because the plates were placed so close together, they blocked certain kinds of fluctuations from happening between them. Meanwhile, the space outside the plates still had all possible quantum fluctuations happening freely. This imbalance in energy created pressure, pushing the plates together. This discovery was revolutionary. It showed that what we thought was nothing was actually full of hidden energy. The Casimir effect gave direct proof that quantum fluctuations were real, and that even a vacuum is never truly empty. Now, this is where things get even more amazing. If the empty space of the universe is full of these tiny bursts of energy, could they have played a role in the birth of the universe itself? Many scientists believe the answer is yes. According to some of the most accepted ideas in modern cosmology, the entire universe may have started from a quantum fluctuation in a very early vacuum. Instead of the universe coming from absolute nothingness, it might have come from a state where energy was already there, hidden, waiting for the right moment. Under the right conditions, one of these quantum fluctuations could have suddenly expanded, causing what we now call the Big Bang. This idea is supported by quantum field theory and the theory of cosmic inflation, which suggest that the universe went through an incredibly fast expansion in its earliest moments. Instead of a universe coming from complete nothingness, it may have burst forth from a quantum vacuum, a place where energy and fluctuations were already bubbling beneath the surface. Even after the Big Bang, quantum fluctuations continued to shape the universe. Right after the universe began, it was unimaginably hot and full of energy. During this time, quantum fluctuations acted like tiny seeds in the fabric of space. At first, these fluctuations were incredibly small, almost impossible to notice. But as the universe expanded, these tiny differences in energy spread out over huge distances. Over billions of years, these tiny variations in energy and density grew under the pull of gravity. Slowly, these fluctuations became the base for galaxies, stars, and planets. Without them, the universe might have stayed smooth and empty, and life as we know it might never have appeared. The idea of cosmic inflation, first suggested by scientist Alan Guth, explains how these quantum fluctuations were stretched to huge scales in the early universe. This rapid expansion magnified the tiny differences in energy, turning them into the large-scale structures we see today. The thought that quantum fluctuations could create a whole universe is both exciting and strange. If our universe came from a quantum fluctuation, could it be only one of many? Some scientists believe that our universe is just one of countless others that may have formed the same way. This leads to the idea of the multiverse, which suggests that quantum fluctuations might be constantly creating new universes, each with its own rules and laws of physics. In this view, what we see as reality might just be a small part of a much larger cosmic landscape, with universes appearing and disappearing all the time. The discovery of quantum fluctuations has overturned the old idea of nothingness. It shows that even in the emptiest parts of space there is hidden, restless energy at work, energy that may have started the universe itself. Even more surprising is the idea that the universe may not need a traditional cause to exist. In our daily lives, everything happens for a reason. Every effect must have a cause. But in the strange and unpredictable world of quantum physics, things can happen on their own, without any clear reason. Particles can appear and disappear. Energy can show up and vanish in an instant. and under the right conditions, a single quantum fluctuation might have created the universe as we know it. This challenges everything we think we know about reality. If the universe could come from quantum fluctuations, does that mean reality itself is built on randomness? The idea that our entire universe might have started from an almost invisible ripple in the fabric of quantum energy is both amazing and mind-expanding. It forces us to face one of the deepest mysteries. How did the universe create itself? Quantum physics, the part of science that studies the tiniest building blocks of reality, gives us a surprising answer. It suggests that what we think of as nothing is not really empty. Instead, it is an unseen, ever-changing space full of hidden energy, always shifting in ways we cannot see. Think of it as a cosmic stage where invisible forces are always at work. Tiny bursts of energy flickering in and out of existence like sparks. These short-lived fluctuations may seem small, but under the right conditions they could act as the first sparks that start something far greater, maybe even a whole universe. Scientists have long studied this idea through quantum field theory, a system that tries to explain how these strange energy shifts work. But this field of study is still young, and many questions remain unanswered. How exactly could these quantum fluctuations have led to the vast and structured universe we see today? What forces guided the change from chaos to order? The truth is, we're only beginning to uncover these cosmic secrets. Still, the idea that our universe could have come from an unseen, quantum-driven event changes our whole view of creation. It gives us a bold and unusual way of thinking, one where the universe may have been born not from an outside force or divine command, but from the strange and powerful properties of space itself. While much is still unknown, one thing is certain. The more we explore, the more we see that reality is far stranger, more complex and more incredible than we ever dreamed. This new way of seeing how the universe began changes everything we once believed about existence. Instead of seeing creation as a single moment that happened billions of years ago, we now see it as an ongoing process, a never-ending cycle of birth and change that happens in the hidden world of quantum physics. In this mysterious world, the line between nothing and something is not as simple as we once thought. What looks like empty space is not empty at all. It is full of unseen energy, waiting for the right conditions to create something new. With this view, the birth of our universe was not a one-time event, but part of an endless rhythm of creation. Think of an unseen cosmic dance, where the chance for new worlds exists in every moment. What scientists call the quantum vacuum, often thought of as a vast empty void, is really a restless sea of energy, constantly bubbling with activity. Even the tiniest shifts in energy can spark the birth of entire galaxies, stars, and planets. As we try to understand where our universe came from, we run into one of the biggest mysteries in modern science, the singularity. This strange point lies at the very center of the Big Bang, and scientists believe that everything we see today, space, time, matter, and energy, came from it. But this leads to an even bigger question. What existed before the Big Bang? Think of a place where the rules of physics stop making sense. A singularity is a point where matter is squeezed into an endlessly tiny space, becoming so dense that gravity becomes unbelievably strong. In this extreme state, space and time twist and collapse in ways we cannot fully understand. Even the most advanced scientific equations, like Einstein's general theory of relativity, cannot describe what happens inside a singularity. This means that, based on what we know now, the laws of physics simply stop working. The singularity that started our universe was even more incredible than the ones found in black holes. Instead of being trapped inside a collapsing star, this singularity marked the very beginning of everything. At that moment, all of existence was squeezed into a tiny, unimaginably hot and dense point, a state where no known physical rules applied. Then, in a single instant, this singularity expanded with enormous power, giving birth to space, time, and all the matter that would later form galaxies, stars, and planets. This explosive event is what we now call the Big Bang. Asking what happened before the Big Bang is hard because it assumes that time already existed. But according to Einstein's theory of relativity, space and time are linked together into one fabric called spacetime. If the Big Bang created spacetime itself, then time as we know it did not exist before that moment. In other words, the very idea of before might not even make sense. However, some scientists think there might be more to the story. Several ideas try to explain what could have come before the Big Bang. Some scientists suggest that the universe did not come from nothing but instead goes through endless cycles of birth, growth, and collapse. In this model, the universe grows for billions of years, reaches a peak, then shrinks back into a singularity before exploding into another Big Bang. If this idea is correct, then something has always existed. Our current universe is just the newest version in a never-ending chain of universes. Quantum physics, the strange science that describes tiny particles, suggests that tiny bits of matter and energy can appear and disappear, even in what seems to be empty space. Some scientists think that the entire universe may have come from one of these random quantum changes. In this view, before the Big Bang, there was a vast emptiness where tiny, unpredictable quantum events happened. At some point, one of these events led to the birth of our universe. Another idea suggests that our universe is just one of many. According to the multiverse theory, countless universes exist, each with its own rules. If this is true, then our universe was not the first and will not be the last. Something has always existed. It just was not necessarily our universe. Before the Big Bang, there may have been another universe, or a completely different state of reality. In the 1970s, brilliant physicists Stephen Hawking and Roger Penrose made groundbreaking discoveries about singularities. By joining Einstein's general relativity with quantum mechanics, the strange rules that control tiny particles, they gained new knowledge about how singularities work. Their studies show that singularities are not just ideas on paper, but real points where physics as we know it breaks down. They proved that if you go back in time to the very start of the universe, you reach a moment where space bends endlessly and time itself stops working in any normal way. This means that before the Big Bang there was no familiar space, no ticking clock, no past, just an impossible state of endless density. Science has given us amazing knowledge about how the universe grew after the Big Bang, but the moment before remains one of the greatest mysteries. If time itself began with the Big Bang, then asking what came before might not make sense at all. However, many scientists believe that we simply have not yet found the right laws of physics to explain what happened. In our daily lives, time feels like an unstoppable river, always moving from one moment to the next. We naturally think in terms of before and after, yesterday, last year, even thousands of years ago. But when we try to use this logic to explain the birth of the universe, things become much more complicated. At the heart of this great mystery is the idea of the singularity, a point where all the known rules of physics stop making sense. Some scientists think that time itself began with the Big Bang, meaning there was no before at all. In this view, asking what happened before the Big Bang would be like asking what lies beyond the North Pole. There is simply no direction left to go. This suggests that time, as we know it, only exists inside our universe and did not exist before it was born. But not all scientists agree. Some believe that the singularity may not have been the true beginning, but instead came from something that already existed. One idea suggests that the universe could have come from tiny random bursts of energy in an empty void, unpredictable changes that somehow sparked the birth of everything. Another idea suggests that our universe is just one in a never-ending cycle, where an older universe collapsed in on itself and then gave birth to a new one. While these ideas are very uncertain and push the limits of human understanding, they open the door to exciting possibilities about what might exist beyond what we can see. One of the greatest minds to explore these mysteries was the famous physicist Stephen Hawking. He spent much of his life studying black holes, strange objects in space where gravity is so strong that nothing, not even light, can escape. Interestingly, the center of a black hole has a singularity, much like the one thought to exist at the beginning of the universe. By studying black holes, scientists hope to uncover secrets about the first moments of existence. In one of his most important discoveries, Hawking revealed that black holes are not completely dark as people once thought. Instead, they slowly release energy in the form of what is now called Hawking radiation. This discovery was surprising because it meant that black holes can shrink over time and eventually disappear. It also raised an even deeper question. When a black hole fades away, what happens to all the information it once contained? Does it truly vanish? Or could there be some hidden way for it to survive? This puzzle challenges our understanding of the universe. The study of singularities, whether inside black holes or at the birth of the universe, reveals a major problem in modern science. The two most powerful theories we have, Einstein's general theory of relativity, which explains gravity and the movement of large objects like planets and galaxies, and quantum mechanics, which describes the tiny world of atoms and particles, do not work together. At the extreme conditions of a singularity, these two great theories fail, leaving scientists searching for a better explanation. Many physicists believe that the missing key is something called quantum gravity, a theory that would combine relativity and quantum mechanics into one complete system. If such a theory were found, it could help us understand what really happens inside a black hole, what took place during the Big Bang, and whether anything existed before it. For many decades, scientists have worked tirelessly to uncover this missing link. They have created countless ideas and built complex mathematical models, but so far no one has been able to fully show how gravity works on the smallest quantum level. This puzzle is important because it prevents us from fully understanding one of the most important events in the history of the universe, the singularity at the birth of everything. The singularity is not just the starting point of our universe, it also represents a wall to our knowledge. It marks the moment when space, time, and matter first appeared, yet it also stands as a barrier that science has not yet broken through. In our everyday lives, we understand reality in simple ways. Things have causes and effects, space has 3 dimensions, and time moves forward like an arrow. But the singularity questions all of these ideas. It forces us to think beyond what we can see, measure, or even fully imagine. What if the laws of physics we rely on only began to exist after the Big Bang? What if time itself, as we know it, was not present before that moment? These questions lead us to some of the oldest and deepest mysteries ever considered by humans. What does it mean to exist? How did something come from nothing? Can we ever truly understand the exact moment when the universe was born? These thoughts have fascinated philosophers, scientists, and thinkers for thousands of years, and they remain at the center of our search for knowledge. As technology improves, we continue pushing the limits of what we know. Powerful telescopes allow us to look deeper into space. Particle colliders help us study the tiniest building blocks of reality, and new ideas try to connect the vast and the tiny into one complete picture. Yet, the singularity remains a mystery, an unsolved puzzle that challenges us to stretch our minds beyond everything we currently understand. It is both an invitation and a challenge, calling us to explore the greatest secrets of the universe and the true nature of reality itself. The anthropic principle is an idea in the study of the universe that says the universe must have the right conditions for life because, if it did not, no one would be here to see it. Simply put, the universe looks perfectly set up for life only because a universe that could not support life would never have thinking beings around to ask about it. People who support the anthropic principle believe this idea helps explain why the universe has a certain age and certain unchanging numbers that make life possible. If these numbers were even a little different, intelligent life might never have appeared. For example, if the universe were much younger, there would not have been enough time for stars to make the heavier elements needed for planets and living things. If it were much older, most stars would have burned out, and star systems like ours might not exist. Scientists have long asked why the basic physical numbers, the fixed values that guide physics, are exactly what they are. The anthropic principle says they must be this way, because only a universe with these conditions could support life. It is not that the universe was made for life, but that life could only happen in a universe with the right setup. There are many ways to understand the anthropic principle. Some thinkers, like the philosopher Nick Bostrom, have listed about 30 different versions of it. Still, they usually fit into 2 main groups: the weak anthropic principle. This says we see a universe fit for life because life only shows up in such a universe. The strong anthropic principle. This says the universe must, in some way, be shaped to create life. The idea came from noticing that the universe's laws and numbers seem perfectly suited for life. It is an argument based on looking back. If the universe could not support life, we would not be here to talk about it. Some people say calling it the anthropic principle is misleading. The word comes from the Greek word anthropos, meaning human, but the idea does not say the universe is made just for humans. Instead, it can apply to any form of life, not only humans or carbon-based creatures. It would work just as well for alien life, stars, or even galaxies. The anthropic principle has led to debates, mainly because different versions of it have been used to argue different things. Some critics feel that the principle stops deeper scientific study. For example, the weak anthropic principle is sometimes seen as unscientific because it cannot be tested or proven wrong. On the other hand, stronger versions make bold claims that are still argued over because they rely on evidence that is hard to check. In the year 1961, physicist Robert Dicke said that the universe must have a certain age fit for life. If it were 1/10 of its current age, elements like carbon would not have had time to form, and planets like Earth would not exist. If the universe were 10 times older, most stars would already be dead, leaving behind mainly white dwarfs and faint red stars, making it unlikely for star systems to survive. Dicke also said that the universe's matter must be close to a critical density, just enough to stop it from collapsing in a big crunch, but not so much that it would prevent it from expanding. Later studies showed that normal matter makes up about 30% of this critical density, while the rest is probably due to dark energy. In the late 20th century, physicist Steven Weinberg gave an anthropic reason for the strange cosmological constant, a number that controls how fast the universe expands. The predicted value of this constant from particle physics is far off from the one we actually see, by about 120 orders of size. This has been called the worst prediction in physics. But Weinberg pointed out that if the cosmological constant were just a little bigger, the universe would have expanded too fast for stars and planets to form, and without them, there would be no life. Some scientists say that the physical numbers controlling the 4 basic forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, seem perfectly balanced to let life exist. If, for example, the strong nuclear force were increased by just 50%, it would change the way elements form in stars, stopping the creation of hydrogen, the key part of water and life as we know it. In the same way, small changes in the other forces would greatly affect the universe's age, shape, and ability to support life. The name anthropic principle was first used by Brandon Carter, a physicist, at a 1973 meeting honouring the 500th birthday of Copernicus. Carter brought up the idea as an answer to the Copernican principle, which says humans do not have a special or central place in the universe. Carter suggested that, even though humans are not the centre of the universe, the conditions we see must still be somewhat special because they allow intelligent life to exist. At that time, the steady-state theory, which said the universe always looked the same and had no beginning, was still popular. But this theory was overturned in 1965 with the finding of the cosmic microwave background radiation, clear proof that the universe has changed over time, most likely starting with the Big Bang. In the year 1973, physicist Brandon Carter explained 2 ideas under what he called the anthropic principle. The first, called the weak anthropic principle, said that humans only exist in certain times and places in the universe because those places happen to be fit for life. The second, more debated idea, the strong anthropic principle, went further. It said the basic numbers of physics, the ones that shape the universe, might be set in a way that makes life possible. At first, the weak version seems reasonable. After all, humans could have developed in many different times and places as long as conditions were right. But the strong version is harder to explain. There is only one known universe with fixed physical laws, so why do those laws allow life at all? Carter gave 2 possible answers. First, humans can make good guesses about the physical numbers of the universe based on the fact that they exist within it. But if that does not seem enough, there is another answer. Maybe there is not just one universe. Maybe there are many, perhaps an endless number, each with its own physical laws. This idea, now called the multiverse theory, though Carter first called it the world ensemble, would mean that our universe is only one among countless others, and we happen to live in one that allows life. This idea is daring, even extreme, but it may help explain a deep puzzle. Why do the laws of physics seem so perfectly balanced for life? If there are countless universes, most would not allow life, but a few would. Naturally, humans would only exist in one of the just right universes, so it should not surprise us that we live in one. Since Carter's paper, the anthropic principle has taken on many different meanings. A big turning point came in the year 1986 when scientists John D. Barrow and Frank Tipler gave new versions of the weak and strong anthropic principles, different from Carter's original ideas, which caused confusion among scientists. But Carter was not the first person to think about such ideas. As early as the year 1904, evolutionary biologist Alfred Russel Wallace suggested that the universe might need to be as huge and complex as it is in order to make a world able to support human life. Then, in the year 1957, physicist Robert Dicke said that the age of the universe is not random. Living conditions decide why we exist at this point in cosmic history. He also said that if the basic numbers of physics were even slightly different, humans would never have existed to ask these questions. Even before these scientists, Austrian physicist Ludwig Boltzmann had thought about similar ideas in the late 19th century. Boltzmann wondered why the universe seemed to have such low entropy, a measure of disorder, when the rules of thermodynamics said it should be much more messy. He suggested that random changes could create short-lived pockets of low entropy, small areas where order briefly appears out of chaos. He argued that humans happen to exist in one of these rare orderly areas, simply because that is the only kind of place where intelligent life could arise. Carter's version of the anthropic principle has led to much debate, partly because it is based on a simple but easy to misunderstand idea. The universe seems finely tuned for life, so maybe it really is. Scientists such as Stephen Hawking and Michael Collins said this might mean that there is not just one universe, but an endless number of universes, each with different starting conditions. If this is true, then the reason our universe looks so finely balanced is simply that we would not be here to notice it otherwise. Most universes would not allow life, but in an endless multiverse, at least a few would, and ours is one of them. Though scientists have wondered about similar ideas for hundreds of years, by the early 1970s the only scientific theory that allowed for many universes was the many worlds interpretation of quantum physics. This theory says that every quantum event creates branching timelines, but it does not allow for changes in the basic physical constants. Since then, however, new theories have appeared. In the 1980s, the mix of inflation theory and symmetry breaking in the early universe gave a possible way for physical constants to change across different parts of space. By the early 21st century, string theory suggested an even more striking idea. What if every basic constant, including the number of space dimensions, could change across an unimaginably huge landscape of possible universes? This idea is very different from the old goal of scientists, to find one complete theory of everything with no free choices. Albert Einstein once asked whether God had any choice in setting the laws of physics. In other words, was the universe meant to be exactly the way it is, or could it have been different? In the year 2002, some scientists working on string theory believed they were close to removing the need for the anthropic principle. But by the next year, scientist Leonard Susskind argued that the opposite might be true, that the great complexity of the landscape of possible universes actually made the anthropic principle seem more believable than ever. The anthropic principle also plays a part in debates about intelligent design. Believers in intelligent design often point to the fine-tuning of the universe as proof of a creator. Critics, however, say that fine-tuning may not be as amazing as it looks. Some think the universe is not really as finely tuned as people claim, while others suggest that even if it is, this does not clearly prove the existence of a higher power. Some even argue that the anthropic principle itself weakens the case for intelligent design, because it gives another reason for why the universe supports life. Brandon Carter's weak anthropic principle is not something that can be tested by looking at it directly. It is more like a guiding idea for scientists. The strong anthropic principle, on the other hand, says that the universe must somehow support life. Testing this would mean finding proof of life in other universes, but since most definitions of universe say we cannot see others, this creates a big problem. The theory might be impossible to prove or disprove. Thinker John Leslie once made a set of predictions based on the strong anthropic principle, saying that the laws of physics will turn out to be set by chance instead of strict rules. Theories about many universes will keep gaining scientific support. More proof that the universe is finely tuned will continue to appear. No forms of life based on non-carbon chemistry will ever be found. Mathematical studies of galaxy formation will show that the universe's expansion rate is crucial for shaping its structure. Some scientists, like Craig Hogan, say it would be very strange if all basic constants were fixed, since that would leave no way to explain fine-tuning. If that were the case, humans might have to accept that the universe just had to be this way to support life, whether we like it or not. The well-known astronomer Fred Hoyle may have used a special way of thinking called anthropic reasoning to make an amazing guess about the stars. He saw that life on Earth depends on a chemical element called carbon, especially a type known as carbon-12. Since carbon is so important for life, he thought there must be an unknown process inside stars that makes it easier for carbon-12 to form. He studied a particular reaction in stars called the triple alpha process, which creates carbon from smaller helium atoms. Based on this idea, Hoyle guessed that there must be a hidden energy level, or resonance, in carbon-12 that makes this process work well. He even worked out that this energy level should be about 7,600,000 electron volts. Soon after, a research team led by Willie Fowler proved that this energy level really did exist, and their results closely matched Hoyle's guess. But in the year 2010, a historian of science named Helge Krag argued that Hoyle had not really used anthropic reasoning when he made his guess in 1953. Krag said that anthropic reasoning, the idea that the universe seems fine-tuned for life, did not become widely discussed until 1980. He claimed that Hoyle and other scientists only made the link between carbon and life after the resonance had already been found. Krag called this idea an anthropic myth. Another interesting debate in cosmology is about the theory of cosmic inflation, which explains how the universe grew extremely fast in its earliest moments. A scientist named Don Page criticized this theory by pointing to a big problem. For time to move forward, the universe had to begin with an incredibly low level of disorder, or entropy. But this starting point seems very unlikely, making the whole inflation theory doubtful. However, scientist Paul Davies disagreed. He said that an inflationary version of the anthropic principle fixes this problem. Davies agreed that the early universe had to be very orderly, a tiny, neat patch of space that later grew into the universe we see now. He believed this actually made the inflation theory stronger, since it removed the need for extra guesses about how the universe began, guesses that other Big Bang theories still need. Another big idea in modern physics comes from string theory, which says that instead of just one universe, there may be a huge number of possible universes. These different universes, called vacua or backgrounds, make up what scientists call the multiverse, or the string landscape. Scientist Leonard Susskind said that if there are countless universes, then anthropic reasoning makes sense, because we only exist in a universe that has the right conditions for life. If other universes do not allow life, we simply never notice them. Famous scientist Steven Weinberg saw the anthropic principle as an important shift in scientific thinking. He thought that cosmologists who do not believe in a divine creator could use the principle to explain why the basic constants of nature seem perfectly suited for life. He called it a turning point in modern science, because it could explain the exact values of these constants without assuming that a higher power carefully adjusted them. But not everyone agreed. Scientists like David Gross, Luboš Motl, Peter Voigt, and Lee Smolin argued that this way of thinking does not really predict anything useful. Meanwhile, researchers such as Max Tegmark, Mario Livio, and Martin Rees noted that many accepted scientific theories cannot be fully tested yet, but they are still seen as valid. Between 2000 and 2002, a scientist named Jürgen Schmierhuber gave another view. He pointed to Ray Solomonoff's theory of universal inductive inference, which gives a logical way to judge scientific theories based on limited observations. Schmierhuber argued that this method already gives scientists the best way to decide which theories are most reliable, even if they cannot test everything directly. Two researchers, Jiwei Wang and Samuel L. Brownstein, studied the idea that life's existence in the universe depends on certain basic physical constants. Their results suggested that if scientists do not fully understand these constants, they might wrongly think that the universe was purposely made for life. This challenges the idea that our universe is uniquely special, because if different constants could also allow life in other universes, then ours may not be as rare as it seems. String theory is a complicated but very interesting idea in physics that says the smallest building blocks of the universe are not just tiny dots, like normal particles, but instead tiny vibrating strings. These strings move through space and affect each other, and the way they vibrate decides the properties of the particles we see, such as their mass and electric charge. If you look at a string from far away, it acts like a normal particle, but up close, it is really a tiny loop or thread. One of the most important predictions of string theory is that one of these vibrations matches the graviton, a particle thought to carry the force of gravity. Because of this, string theory is seen as a possible explanation for quantum gravity, which tries to combine gravity with the strange and powerful rules of quantum mechanics. Scientists are interested in string theory because it offers a possible way to answer some of the deepest mysteries in physics. Over the years, it has helped researchers make progress in understanding black holes, the early universe, and even the forces inside atoms. It has also influenced math research in surprising ways. But the biggest reason string theory is so exciting is that it could be a theory of everything, a single idea that explains all the basic forces of nature, including gravity, electricity and magnetism, and the nuclear forces that hold atoms together. However, even after many decades of study, scientists are still trying to find out whether string theory really describes the real universe, or if it allows for too many possibilities to make clear predictions. String theory first appeared in the late 1960s as a way to explain the strong nuclear force, which holds atomic nuclei together. But when another theory, quantum chromodynamics, was found to explain it better, scientists set string theory aside. However, they later saw that string theory had surprising features that made it a strong candidate for explaining gravity at the quantum level. The first version of string theory, called bosonic string theory, only included one type of particle called bosons. Later, the theory grew into what is now called superstring theory, which brought in the idea of supersymmetry. This idea suggests a close link between bosons and another type of particle called fermions. Over time, physicists found 5 different versions of superstring theory. But in the mid-1990s, they found strong evidence that all 5 were actually different views of one bigger theory, called M theory, which needs a universe with 11 dimensions instead of the usual 3 dimensions of space and 1 of time. In the late 1990s, scientists also found an important connection called the anti-de Sitter conformal field theory, ADA's CFT correspondence. This discovery linked string theory to another major area of physics, quantum field theory, showing that the two could give new insights into each other. One of the biggest problems with string theory is that scientists still do not have a full and clear explanation of the whole theory in every case. Another problem is that string theory predicts a huge number of possible universes, making it hard to know which version, if any, matches our own. These problems have led some physicists to ask whether string theory is really the right path, or if too much work is being put into an idea that may never be tested. In the 20th century, physicists built 2 major theories that explain the universe. The first was Albert Einstein's general theory of relativity, which describes gravity and the shape of space and time on a large scale, such as planets, stars, and galaxies. The second was quantum mechanics, which explains the strange behavior of tiny particles like electrons and photons. By the late 1970s, these 2 theories were enough to explain almost everything seen in nature, from the smallest particles to the growth of the whole universe. However, despite their success, there was a huge problem. These 2 theories do not work well together. General relativity is based on normal physics, while quantum mechanics follows very different rules. To fully understand the universe, scientists need a quantum theory of gravity, but attempts to combine the two have faced big problems. String theory is one of the most promising ideas for solving this puzzle, but it is still unfinished. String theory starts with an exciting idea. What if the tiny particles we think of as points in space are actually tiny vibrating strings? Instead of treating them as dots with no size, string theory imagines them as very small, one-dimensional threads that move and shake in space. These strings can be either open, like a short line, or closed, forming a tiny loop. The way they vibrate decides their properties, like their mass, charge, and how they interact with other particles. From a distance, these vibrating strings look just like the basic particles physicists already study, fitting into existing models of physics. But when observed on extremely small scales, smaller than anything we can measure right now, they act in a way that could explain mysteries of the universe. One of the most exciting possibilities is that one of these vibrations matches the graviton, a possible particle thought to carry the force of gravity. If true, this would mean that string theory naturally includes gravity, something no other main theory of physics has done. Over the past several decades, physicists working on string theory have made an important finding. Different versions of the theory, which at first seem separate, are actually connected through math links called dualities. These dualities show that what looks like one type of theory from one view may actually be another type when seen differently. This finding led to the idea that all consistent versions of string theory might be part of a bigger united framework called M-theory. However, no one fully understands what M-theory really is yet. It is still unfinished. String theory has also given surprising ideas about black holes and the nature of gravity. For decades, physicists have struggled with strange problems that appear when trying to apply quantum mechanics to black holes. In the late 1990s, a breakthrough came with the discovery of the anti-de Sitter conformal field theory correspondence, often called AD-CFT correspondence. This discovery linked string theory to other well-known areas of physics, helping scientists study black holes in new ways. AD-CFT has even found uses in areas outside of gravity, such as nuclear physics and condensed matter physics, which study how particles behave in extreme conditions. Because string theory tries to include all the basic forces of nature, including gravity, it has been suggested as a possible theory of everything. Many physicists hope that if string theory can be fully worked out, it will give a complete explanation of the universe, including why particles have the masses and charges they do, how dark matter fits in, and even how the early universe grew. However, there are still big problems. Physicists do not yet know whether string theory really describes our universe, or whether it allows for many different possible universes. One of the biggest problems in string theory is that it is not fully understood in all cases. The easiest way to study how strings behave is through a math method called perturbation theory, which works by making small guesses. However, this method does not show everything about string theory, and physicists do not yet know how to explain the theory in its full form without these guesses. Another unsolved problem is how string theory sets the vacuum state, the basic state of the universe. Without this knowledge, it is unclear how much freedom the theory has in shaping the universe we see today. Some critics say that these unanswered questions make string theory too uncertain, while others believe it is still worth studying. To see where string theory fits into modern physics, it helps to look at quantum field theory, the base of particle physics. Quantum field theory is the math system used to describe tiny particles, treating them as ripples in underlying fields. In this theory, scientists work out chances of particle interactions using a method called perturbation theory, which was created in the early 20th century by physicists like Richard Feynman. A key tool in this method is Feynman diagrams, which are drawings that help show how particles interact. String theory builds on these ideas but makes a bold change. Instead of picturing particles as points moving through space, it describes them as tiny strings. In traditional quantum field theory, a Feynman diagram shows a particle's path as a one-dimensional line. In string theory, this line is replaced by a two-dimensional surface, showing the path of a vibrating string. This change changes the math and could explain things quantum field theory struggles with, such as gravity. However, one major problem remains. String theory does not yet have a full explanation beyond perturbation theory, making it hard to answer all the questions physicists want to explore. One of the most important parts of string theory is the scale at which it works. The length of a basic string is thought to be about 1/10,000,000th of a trillionth of a trillionth of a meter, the Planck length. This is so incredibly small that, at the scales we can study in experiments, these strings would look like tiny points. Only at the Planck scale do the effects of quantum gravity become important, making string theory a possible explanation for how gravity works at the smallest levels. At first, string theory was developed as bosonic string theory, which focused only on bosons, the particles that carry forces like photons in electricity and magnetism. However, this version had serious problems, so scientists expanded the idea into superstring theory, which includes both bosons and fermions, the particles that make up matter like electrons and quarks. Superstring theory also uses supersymmetry, an idea that suggests every force-carrying boson has a matching matter particle, fermion, and the other way around. There are 5 main versions of superstring theory: Type 1, Type 2, A, Type 2b, and 2 types of heterotic string theory. Each version allows for different types of strings, and at lower energy levels they produce different physical properties. For example, Type 1 string theory includes both open strings, which have loose ends, and closed strings, which form loops, while the other versions focus only on closed strings. In our daily experience, we know 3 dimensions that describe space: height, width, and length. These 3 dimensions help us understand the shape and size of things around us. However, Albert Einstein's groundbreaking theory of general relativity introduced a shocking idea. Time is not separate from space, but is actually a 4th dimension. Together they form what scientists call spacetime, a 4-dimensional fabric that shapes the very structure of the universe. In this model, gravity is not just a force pulling objects toward each other, as Isaac Newton once thought. Instead, gravity comes from the way spacetime bends and curves around heavy objects like planets and stars. Even though this 4-dimensional spacetime model explains a lot about how the universe works, scientists often explore theories that involve even more dimensions. Sometimes, adding extra dimensions makes difficult math problems easier to solve, helping physicists understand the universe better. In fact, certain scientific areas, like condensed matter physics, which studies how materials behave, can be described using theories with just 2 or 3 dimensions. But what if the universe really has more than 4 dimensions, and we just have not seen them yet? Some theories suggest that extra dimensions might exist, hidden in ways we cannot easily notice. One of the most fascinating ideas in modern physics is string theory. This theory says that, at the deepest level, everything in the universe is made of tiny, vibrating strings instead of point-like particles. But for string theory to make sense in math, it needs extra dimensions beyond the 4 we know. Different types of string theory suggest different numbers of dimensions. Bosonic string theory says spacetime has 26 dimensions. Superstring theory needs 10 dimensions, and a more advanced version called M-theory says there are 11 dimensions. But if these extra dimensions are real, why don't we see them? One possible answer is a concept called compactification. This idea says that the extra dimensions are curled up so tightly that they are too small for us to notice. Looking at a garden hose from far away, it might seem like a simple line, but if you get closer, you see it has a 2nd dimension, its round width. An ant crawling on the hose would feel both dimensions, but from far away they seem hidden. In the same way, if extra dimensions exist, they might be curled up so small that we don't see them in everyday life. To describe the universe correctly using string theory, these extra dimensions must be curled up in a very specific way. Scientists think they must take the shape of a special, 6-dimensional structure called a Calabi-Yau manifold. This shape is named after the mathematicians Eugenio Calabi and Xingtung Yau, who studied it. Only certain types of Calabi-Yau shapes would let string theory properly describe the basic forces of nature, like electromagnetism, the weak and strong nuclear forces, and gravity. Another interesting way to think about extra dimensions is through something called the brain world idea. In this view, our whole universe is really a 4-dimensional brain floating inside a higher dimensional space. Think of a soap bubble floating in the air. The surface of the bubble is like our universe, while the air around it represents extra dimensions we cannot directly see. According to this idea, particles and forces like electromagnetism stay inside our 4-dimensional universe, but gravity might spread into the extra dimensions. This could explain why gravity is much weaker than the other basic forces. It might be leaking into hidden dimensions. String theory also includes the idea of duality, which means that theories that look very different might actually be 2 sides of the same coin. One type of duality, called S-duality, says that a group of particles that strongly interact, often colliding and combining, in one theory can be described as weakly interacting, rarely colliding, in another theory. This means that complex physical interactions might have simpler explanations from another point of view. For example, type 1 string theory is mathematically equal to another theory called the SO32 heterotic string theory through S-duality. Another type of duality, called T-duality, deals with how strings behave in curled-up extra dimensions. It says that if a string moves around a circular dimension of a certain size, it can act just like a string moving around a much smaller circle. This means that a universe with large extra dimensions might look the same as one with very small extra dimensions. Type 2a and Type 2b string theories, for instance, are actually equal through T-duality, even though they look different at first. Duality is a powerful idea that shows up not just in string theory, but in other areas of physics too. A well-known example is the AD-CFT connection, which links string theory to quantum field theory. This surprising link has given new ideas about how particles and forces behave at the smallest levels. In simple words, when 2 theories are related by duality, it means that if you change one theory in a certain way, it will end up looking just like the other. Even though they seem different at first, they are really describing the same reality using different types of math. Another important idea in string theory is the idea of branes. A brane, short for membrane, is a multi-dimensional object that stretches the idea of a point particle into higher dimensions. A zero-dimensional brane is just a point, a one-dimensional brane is a string, and higher dimensional branes are called p-branes, where p stands for the number of space dimensions. These branes move through space-time according to the rules of quantum mechanics and can have features like mass and charge. They also interact with basic fields, just like how charged particles interact with electric and magnetic fields. A special type of brane, called a D-brane, plays an important role in string theory. Open strings, strings with two loose ends, must have their ends attached to a D-brane. The D stands for Dirichlet boundary conditions, a math rule that controls how the strings behave. D-branes have been key in discoveries like the AD-CFD connection, which has helped explain many puzzles in quantum physics. The universe is full of mysteries, and one of the biggest is dark energy. This strange force is what makes the universe expand faster and faster. Scientists think that dark energy makes up about 68% of everything in the universe. In comparison, dark matter, another hidden substance, makes up about 26%, while all the normal matter, the stars, planets, and everything we can see, only adds up to about 5%. Other forms of energy, such as light particles, photons, and neutrinos, are so small in comparison that they hardly matter. Even though dark energy has an extremely low weight, about 7 times 10 to the power of negative 30 grams in every cubic centimetre, it still controls the universe. This is because, unlike matter, which gathers together into galaxies and stars, dark energy is spread out evenly across space. No matter where you go in the universe, dark energy is always there, filling every part of space. Scientists first thought dark energy might exist when they studied faraway exploding stars known as type Ia supernovae. These supernovae act like cosmic measuring sticks because they shine with the same brightness no matter how far away they are. By watching how their light stretches as it travels through space, a process called redshift, scientists can figure out how quickly they're moving away. What they found was shocking. Instead of slowing down, the universe was expanding faster and faster. This was the opposite of what scientists expected. Before this discovery, most believed that gravity from all the matter in the universe would slowly slow down the expansion, much like how a thrown ball slows before falling back to the ground. But the data showed that some unknown force, was pushing the universe apart. That force was later called dark energy. There are several ideas about what dark energy could be. One main idea is called the cosmological constant. This says that dark energy is a steady, unchanging force that fills space. It is sometimes described as the energy of empty space, or vacuum energy. Another idea is that dark energy comes from scalar fields, a type of energy that changes over time and space. These fields could act differently in different parts of the universe, making dark energy more changeable. Some versions of this idea include quintessence and moduli fields. Other theories suggest that dark energy could interact with gravity in ways we do not yet understand. One idea, called cosmological coupling, suggests that dark energy and gravity might be connected in some unknown way. Another idea, interacting dark energy, suggests that dark energy might be affected by other unseen forces in the universe. The idea of a strange energy filling space actually goes back to Albert Einstein. In the early 20th century, Einstein added something called the cosmological constant, lambda, into his equations of general relativity. At the time, scientists thought the universe was still, neither expanding nor shrinking. To make his equations fit this view, Einstein added the cosmological constant, which acted as a force pushing against gravity, stopping the universe from collapsing in on itself. But in the year 1929, the astronomer Edwin Hubble discovered that the universe was not still at all. It was actually expanding. This made Einstein see that his first idea was wrong. He later called the cosmological constant his greatest mistake. Ironically, many decades later, scientists found that a repelling force, what we now call dark energy, was indeed pushing the universe apart, meaning Einstein's idea may not have been a mistake after all. In the year 1980, physicists Alan Guth and Alexei Starobinsky suggested a new idea called cosmic inflation. This idea says that just after the Big Bang, the universe went through a very short but extremely fast growth, expanding at an incredible speed. This inflation period shaped the structure of the universe and explains why galaxies are spread out the way they are today. Inflation looks a lot like dark energy, since both involve very fast expansion of space. But the energy behind inflation was much stronger than the dark energy we see today. Scientists are still trying to understand if these two forces are connected or completely separate. By the 1980s, scientists had built models of the universe that relied heavily on cold dark matter, a form of dark matter that moves slowly compared to the speed of light. These models did a good job explaining how galaxies formed, but they had some problems. For example, they predicted a slower Hubble constant, the rate of the universe's expansion, than what astronomers actually observed. The situation changed in the year 1992, when NASA's COBE spacecraft found small irregularities in the cosmic microwave background, the faint glow left over from the Big Bang. This discovery pushed scientists to rethink their models. A major turning point came in the year 1998, when astronomers studying faraway supernova found clear proof that the universe's expansion was speeding up, not slowing down. This was the first direct proof that dark energy was real. More discoveries followed. In the early 2000s, experiments like Boomerang and Maxima studied the cosmic microwave background and found that the universe's total energy density was very close to what is known as the critical density, the exact amount needed to make the universe flat on large scales. But when scientists measured the amount of matter in the universe, they found it was only about 30% of this critical density. The missing energy was explained by dark energy. Further proof came from the 2-degree field galaxy redshift survey in the year 2001, which measured the spread of galaxies and showed that dark energy was needed to explain the results. Then, from the year 2003 to the year 2010, NASA's WMAP satellite gave even more exact measurements of the cosmic microwave background, strengthening the Lambda-CDM model as the best explanation for how the universe is built and how it changes. The name dark energy was first used in the year 1998 by physicist Michael S. Turner, following the earlier term dark matter, which had been introduced by Fritz Zwicky in the 1930s. Despite all these discoveries, dark energy remains one of the biggest mysteries in modern physics. Some scientists think it could be a basic property of space itself. Others think it might be linked to quantum mechanics, the strange rules that control particles at the tiniest scales. Future experiments, including new space telescopes and large galaxy surveys, aim to find more clues about this strange force. To truly understand how the universe grows and stretches over time, scientists need to take very exact measurements of its expansion. In the world of general relativity, researchers figure out how fast the universe is expanding by studying its shape and a key idea known as the cosmological equation of state. This equation explains how things like temperature, pressure, and the combined amounts of matter, energy, and vacuum energy work together in different parts of space. One of the biggest challenges in modern cosmology is working out the equation of state for dark energy. Scientists believe dark energy plays a major role in the universe's rapid expansion, but its true nature is still unknown. To study this, researchers include the cosmological constant in the Standard Model of Cosmology, also called the Friedmann-Lemaitre-Robertson-Walker model. This leads to what experts call the Lambda Cold Dark Matter model, or Lambda-CDM model. It is often called the gold standard of cosmology because it closely matches what we actually see in the universe. Since the year 2013, the Lambda-CDM model has been tested many times through very exact observations, including data from the Planck spacecraft and the Supernova Legacy Survey. Early results from this survey suggested that dark energy acts almost exactly as Einstein's cosmological constant predicts, with an accuracy of about 10%. More recent findings from the Hubble Space Telescope's Higher Z team show that dark energy has been affecting the universe for at least 9 billion years, long before the universe began its rapid speeding up. Yet, despite these findings, dark energy remains one of the greatest mysteries in physics. It seems to be very smooth and evenly spread across space, with an extremely low density. Unlike other forms of energy or matter, it does not seem to interact with anything except gravity. Its density is unbelievably small, about 1 divided by 10 followed by 27 zeros kilograms in every cubic meter, making it almost impossible to detect in lab experiments. Yet, even though it is so weak, dark energy makes up about 68% of the universe's total energy. This is because, unlike matter, which clumps together, dark energy spreads out evenly across all of space, deeply affecting the universe's expansion. One main explanation for dark energy connects it to something called vacuum energy. This refers to the tiny changes of particles and antiparticles that constantly appear and disappear in empty space, following Heisenberg's uncertainty principle. According to Einstein's theory of relativity, this vacuum energy should have a gravitational effect, meaning it adds to the cosmological constant. This, in turn, is believed to be one of the main reasons the universe's expansion is speeding up. But there is a huge problem. When physicists use quantum field theory to predict how much vacuum energy should exist, they get a number that is far greater than what is actually seen. This huge gap between theory and reality remains one of the biggest unsolved problems in modern physics. Regardless of what dark energy really is, for it to cause the faster spreading of the universe, it must have a very strong pushing force in the opposite direction called negative pressure. In general relativity, pressure acts in a similar way to mass when it comes to its pull by gravity. Both pressure and mass are part of something called the stress-energy tensor, which decides how matter and energy affect gravity. In the case of dark energy, this opposite pressure works against gravity, making space spread out faster and faster. If the universe were shrinking instead, this same pressure would slow down its squeezing. This effect is sometimes called gravitational pushing away, because it seems to force everything apart, working against the normal pull of gravity. When we break down the universe into its main parts, we see that everything we know fits into three wide groups: matter, radiation, and dark energy. Matter includes everything that has weight, from stars and planets to tiny dust grains. As the universe spreads, the energy of matter thins out in proportion to the cube of the spreading factor. Think of a box filled with particles. If the box becomes twice as large, the energy of the particles inside does not just get cut in half, it goes down by a factor of 8 because the space inside grows in 3 directions. Radiation, which includes light and heat, acts a little differently. As space spreads, the energy of radiation drops even faster than that of matter. This is because, apart from spreading over a bigger space, the waves of light and radiation also get stretched. This stretching, called redshift, makes the radiation lose energy quicker than matter does. Dark energy, however, works in a completely different way. Unlike matter and radiation, its energy does not get thinner as the universe grows. Instead, it stays the same, no matter how big the universe becomes. In simple terms, while matter spreads out as space grows, dark energy stays steady, filling the empty space evenly and pushing the universe to expand faster. Scientists have collected many pieces of evidence that show dark energy exists, even though it has not been directly found. Distance and redshift measurements. By studying how light from faraway objects has stretched over time, scientists discovered that the universe has been expanding faster in recent times than it did long ago. This shows that something, likely dark energy, is causing this faster growth. The need for extra energy. The universe looks flat in shape, meaning it does not bend inward or outward. For the universe to be flat, there must be a certain amount of total energy. Since normal matter and dark matter together are not enough, scientists believe dark energy must be filling the gap. Patterns in cosmic structures. When astronomers study the large-scale layout of galaxies, they see patterns that hint at the role of dark energy. The way galaxies are spread across space gives more clues about the universe's expansion and the strange force behind it. In the year 1998, a group of astronomers called the High Z Supernova Search Team made a shocking discovery while studying a special kind of exploding star known as Type Ia supernovae. They thought they would find that the universe's expansion was slowing down because of gravity, but instead they found the opposite. It was speeding up. Just 1 year later, in 1999, another group of scientists, the Supernova Cosmology Project, reached the same surprising result. Their important work changed our understanding of the universe and earned them the Nobel Prize in Physics in 2011. Since then, many more studies have confirmed this finding. Studies of the cosmic microwave background, the faint glow left over from the Big Bang, have given strong evidence. astronomers have also looked at how light bends around huge objects in space, called gravitational lensing, and how galaxies are spread out. All these findings support the idea that a strange force called dark energy is driving the faster growth of the universe. Some doubters argue that the strongest evidence comes only from measuring redshift, how light stretches as objects move away, and the distances of supernovae. But other evidence, such as patterns in the cosmic microwave background, also shows that the universe is expanding faster than it would without dark energy. Supernovae are very useful for studying the universe because they act like natural measuring tools, often called standard candles. Scientists know exactly how bright these explosions should be, which helps them tell how far away they are. By comparing a supernova's distance with how much its light has stretched, its redshift, astronomers can measure how quickly the universe is expanding. Type Ia supernovae are especially valuable because they always explode with the same brightness, making them among the most trusted cosmic markers. Recent studies show that dark energy makes up about 71% of the universe, while the other 29% is made of dark matter and normal matter. The main idea that explains how galaxies, stars, and other cosmic structures form says that matter only makes up about 30% of the universe's total critical density, the amount needed for the universe to stay flat. More evidence of dark energy came in 2011 from the Wigglesy Galaxy Survey, which studied more than 200,000 galaxies. Scientists used a new method to measure distances to galaxies as far as 2 billion parsecs away. Their results confirmed that the universe has been expanding faster, giving even stronger evidence for cosmic speeding up. For the universe to be as flat as it looks, there must be extra energy filling space. All the visible matter, both normal and dark, makes up only about 30% of what is needed. The other 70% is believed to be dark energy. Data from the Wilkinson Microwave Anisotropy probe, which mapped the early universe, showed that dark energy makes up about 73%. Later findings from the Planck satellite updated this, showing that dark energy makes up about 68%, dark matter about 27%, and normal matter just under 5%. Dark energy also helps explain strange patterns in the cosmic microwave background. When light particles, called photons, travel through regions of strong gravity, like galaxy clusters or empty spaces, they gain or lose energy. This makes temperature changes in the background radiation and is known as the integrated Sachs-Wolf effect. It is seen as another strong clue of dark energy. Scientists are also using a new method to study dark energy by measuring the Hubble constant, which shows how the universe's growth rate changes over time. They study galaxies that have grown in a steady way, treating them like cosmic clocks. By looking at their ages and redshifts, they can estimate how fast the universe was growing at different times. Even with all this evidence, dark energy is still one of the biggest unsolved puzzles in physics. Scientists agree it plays a key role in making the universe expand faster, but they do not fully know what it is or how it works. To find answers, some are rechecking Einstein's theory of gravity to see if changes are needed. Others are studying the exact features of dark energy, while some are even looking at other possible reasons based on new cosmic discoveries. One of the simplest ideas about dark energy is that it is a basic part of space itself. In this view, even completely empty space holds a form of energy, often called vacuum energy. This idea is known as the cosmological constant and is shown by the Greek letter lambda. It is the base of the Lambda-CDM model, which is now the most accepted idea of the universe's structure. Since Einstein's famous equation shows that energy and mass are linked, this vacuum energy should also have a gravitational effect, changing how the universe grows. But there is a very big problem with this idea. Calculations from quantum physics suggest that the amount of vacuum energy should be unbelievably large, about 120 orders of magnitude higher than what we actually see. If that were true, the universe would have expanded so quickly that galaxies, stars, and planets could never have formed. Yet here we are, in a universe where galaxies and stars have formed and changed over billions of years. Something must be cancelling out most of this energy, but not all of it. Scientists do not yet know why, making dark energy one of the greatest mysteries in today's physics. While many believe dark energy is a constant, unchanging force, some scientists think it could be something much more active, an energy field that changes over time. This idea is called quintessence. Unlike the cosmological constant, which stays the same everywhere, quintessence acts like an energy field spread across the universe, affecting its growth in different ways at different times. It is thought to be extremely light so that, unlike normal matter, it does not gather into stars and galaxies. Some versions of this idea suggest the universe's expansion is happening a little slower than the standard model says. But so far there is no strong evidence to fully support or reject this idea. One of the biggest unanswered questions about dark energy is why it became the main influence at this particular time in the history of the universe. If it had taken over too early, the universe's fast expansion could have stopped galaxies from forming, and life as we know it might never have existed. Some scientists think this is just a coincidence, while others believe it supports a controversial idea called the Anthropic principle, the idea that the universe must be the way it is because we are here to see it. Interestingly, some quintessence models include a built-in system called a tracker that naturally explains why dark energy became important at this exact time. According to these models, dark energy's behavior is linked to the amount of radiation in the early universe, which could explain why it appeared later, but with strong effects. Some extreme versions of quintessence predict even stranger situations. One of these is phantom energy, a type of dark energy that gets stronger over time instead of staying the same. If this idea is correct, the universe would not just keep expanding, it could eventually be torn apart in a frightening event called the Big Rip. In this doomsday scenario, the force of expansion would grow so strong that it would first tear apart galaxies, then stars, then planets, and finally even atoms themselves, leaving everything as nothing. Another version of quintessence, called K-essence, suggests that dark energy could be made of unusual forms of energy that act in ways never seen before. Some types of K-essence even suggest the existence of negative kinetic energy, which could have strange and unpredictable effects on the universe's growth. In recent years, astronomers have found differences in measurements of how fast the universe is expanding. This disagreement, called the Hubble tension, suggests that the standard model of cosmology might be missing something important. Some researchers think that only certain types of quintessence models, with extra interactions, can explain this difference. Even though dark energy is still one of the biggest mysteries in modern physics, it is closely linked to Albert Einstein's theory of general relativity. Some scientists say that if general relativity were changed in certain ways, we might not need dark energy at all to explain the universe's faster expansion. Several alternative ideas have been suggested, but so far none have been fully proven. In fact, an important discovery, the detection of gravitational waves from the event known as GW 170817, has already ruled out many of these change gravity ideas. According to astrophysicist Ethan Siegel, even though new ideas about dark energy often grab headlines, most scientists still think dark energy is real. Competing theories simply cannot explain what we actually see in the universe as well as the current model does. Scientists believe that the universe's expansion began to speed up about 5 billion years ago. Before that, gravity, mainly coming from dark matter and regular matter, was slowing everything down. But as the universe grew larger, dark matter spread out and became less powerful, while dark energy stayed almost constant. Over time, dark energy became the dominant force, pushing the universe to expand faster and faster. Every time the universe doubles in size, the amount of dark matter in any given area is cut in half, yet dark energy remains nearly the same, filling space evenly. What happens in the future depends entirely on the nature of dark energy. If it stays steady, as the cosmological constant suggests, the universe will keep expanding forever. Galaxies far away will move away from us faster and faster, eventually exceeding the speed of light. This might sound impossible, but it does not break the laws of physics, because it is not the galaxies themselves moving through space, it is space itself stretching. Currently, scientists estimate that the cosmological event horizon, the distance beyond which we can never receive light or any signals, is about 16 billion light-years away. If something happens inside that distance, its light might still reach us at some point in the future. But anything beyond that boundary is lost to us forever. As galaxies get closer to this horizon, the light they send out will be stretched into longer wavelengths, eventually fading from view. In the far future, observers would see those galaxies slowly disappear, leaving only our own local group of galaxies in a vast, dark and empty universe. While the idea of a forever expanding, lonely universe can feel unsettling, some alternative theories imagine even more dramatic endings. If dark energy grows stronger over time, the universe could experience a big rip, tearing apart everything, from galaxies to atoms. Other theories suggest that dark energy might change its strength over time, potentially reversing the expansion. In that scenario, the universe could stop growing and start shrinking in a big crunch, collapsing back into a single point, possibly setting the stage for a new Big Bang and a brand new universe. Another possibility is that dark energy could act in cycles, causing the universe to expand and shrink over and over again, creating endless loops of Big Bangs and Big Crunches. In this view, the cosmos might be caught in a never-ending rhythm of birth, growth, collapse, and rebirth, a cosmic heartbeat stretching across unimaginable spans of time. Loop quantum cosmology, often shortened to LQC, is a fascinating and advanced theory that emerges from a bigger framework known as loop quantum gravity, or LQG. Think of LQC as a simplified, more manageable version of this vast theory, one that focuses specifically on the universe as a whole, rather than the detailed behavior of every particle and field. What makes LQC particularly exciting is that it predicts a kind of quantum bridge, connecting two different phases of the universe, a contracting phase where the universe shrinks, and an expanding phase where it grows. This idea of a bridge is entirely new compared to the classical view of cosmology, which traditionally begins with a singularity, the so-called Big Bang, a point where all known laws of physics break down. LQC offers a picture in which the universe never truly hits a singularity. Instead, it rebounds from an extremely dense state, a phenomenon called a quantum bounce. At the heart of LQC is the influence of quantum geometry, a central concept from loop quantum gravity. In simple terms, quantum geometry suggests that space and time are not continuous and infinitely divisible, as we usually think of them in classical physics, but instead are made up of tiny, discrete building blocks. Imagine a digital image. Up close, it is made of individual pixels, but from afar it appears smooth. Similarly, at everyday scales, spacetime looks smooth and continuous, but when we reach the incredibly tiny Planck scale, about 100 millionth of a billionth of a billionth of a meter, its granular nature becomes important. These discrete units of geometry create a new kind of force, a repulsive force that only becomes significant when the universe reaches extremely high densities and curvatures. At low energies and normal conditions, this force is negligible, and the universe behaves just as Einstein's general relativity predicts. However, as the universe contracts toward what would classically be a singularity, this repulsive force becomes overwhelmingly strong. It effectively pushes back against the crushing pull of gravity, preventing the formation of a singularity and causing the universe to rebound in a big bounce. This discovery dramatically alters the way scientists think about the beginning of the universe and its earliest moments. Many of the classical puzzles of cosmology, such as the horizon problem, which asks why distant regions of the universe look so similar despite apparently never having been in contact, must be reconsidered from this new perspective. Because LQC replaces the classical singularity with a bounce, the universe's history is more continuous, and the extreme conditions at the beginning of the universe can be described using new, well-defined physics instead of unknown infinities. The predictions of LQC are closely tied to the quantum properties of geometry, which is the foundation of loop quantum gravity. In LQG, geometric quantities such as area and volume are not smooth and continuous, but have a fundamental discreteness. This discreteness plays a crucial role in the quantum dynamics of the universe. When the density and curvature of spacetime are far below the Planck scale, LQC's predictions closely match those of traditional quantum cosmology methods such as quantum geometrodynamics. But when the universe reaches densities near the Planck scale, the differences become striking. Classical general relativity would predict a singularity, while LQC predicts a bounce, showing that the early universe behaves very differently once quantum effects are properly accounted for. Since its beginnings, loop quantum cosmology has achieved many remarkable successes. One of these is providing a potential mechanism for cosmic inflation, the rapid expansion of the universe in its earliest moments, which explains why the universe appears so uniform and smooth today. Another success is the complete resolution of gravitational singularities. By replacing the Big Bang with a quantum bounce, LQC removes the mathematical infinities that have long troubled cosmologists. Additionally, scientists have been able to develop effective semi-classical Hamiltonians, mathematical tools that allow them to approximate and understand the behavior of the universe even when quantum effects are extremely strong. These advances have made LQC a dynamic and exciting field of research in modern physics. The story of loop quantum cosmology began in the year 1999, when physicist Martin Boijewald laid its foundations. Over the following years, researchers such as Abhay Ashtekar, Jerzy Lewandowski, Tomasz Pawłowski, and Parampreet Singh greatly advanced the field, refining the theory and exploring its implications. By the end of the year 2012, LQC had grown into a very active area of physics research, with around 300 papers published on the subject. Around the same time, Carlo Rovelli and his colleagues began investigating how LQC might relate to spin foam cosmology, another approach within loop quantum gravity that uses a different mathematical structure to describe the evolution of spacetime. Despite these achievements, there are important caveats to keep in mind. The results obtained in LQC are derived from a simplified or truncated version of classical general relativity, which is then quantized. Because of this simplification, it is possible that the full, untruncated theory might behave differently. Some critics argue that the mechanisms preventing singularities in LQC may rely on features specific to these simplified models, and that the complete, unrestricted theory could avoid singularities in a more subtle way. Nevertheless, LQC provides a powerful and intuitive way to explore the effects of quantum gravity on cosmology, offering insights that would be difficult to gain from the full, complex theory alone. A key feature of LQC is that the replacement of the Big Bang with a bounce does not require any special assumptions about the types of matter present in the early universe, nor does it rely on fine-tuning of initial conditions. This universality makes the quantum bounce a very robust prediction. Furthermore, LQC allows for an effective description of spacetime that captures the underlying quantum dynamics in a form that is easier to work with. This so-called effective dynamics approach has been widely used to model the physics of the Planck scale and the earliest moments of cosmic evolution. Rigorous numerical simulations have confirmed that the effective dynamics closely approximates the full quantum dynamics of LQC, providing confidence that the simplified calculations capture the essential behavior of the universe at these extreme scales. Interestingly, the effective dynamics remains accurate for nearly all situations, except when quantum fluctuations are extremely large at late times. In such cases, the states do not correspond to universes that resemble the macroscopic cosmos described by general relativity, and the effective approach slightly overestimates the density at the bounce. Even then, the qualitative features of the quantum evolution, such as the existence of the bounce itself and the general behavior of the universe before and after it, remain well represented. This demonstrates the robustness of LQC as a model for understanding the earliest universe. Another fascinating aspect of LQC arises when considering scale-invariant geometries, where space-time and matter have no preferred scale. Scale invariance has been proposed as a way to tackle long-standing problems in physics, such as the problem of time, the Immersi ambiguity in loop quantum gravity, and the hierarchy of fundamental forces. In a scale-invariant version of LQC, the discrete structure of spacetime, the tiny building blocks that normally create the quantum bounce, may no longer have a well-defined minimum size. In such scenarios, the Big Bang might not be replaced by a bounce, showing that subtle changes in the underlying assumptions can lead to dramatically different cosmological outcomes.